Good morning, everybody. It's a big pleasure to open this the first morning session of today. The 15th of June is the second day of the conference, New Times, dedicated to new trends in material science and engineering. It's a virtual conference. Unfortunately, I hope that the next time will be possible to meet in person. This session is dedicated to advanced materials for energy conversion. In this session, we will have 5 talks. The first one is a keynote talk from Professor Francesco Paolucci, University of Bologna, which will present his talk about carbon-based hierarchical nanostructure for the electrocatalysis. Then we have 4 invited talks from Professor Piero Torelli in Trieste, CNR, and Professor Lishuet Zhang from Qingdao University, and Alessandra Sansone from CNR Faenza, and the last invited is Professor Andrea Alberti from Politecnico Turin. I think this session is particularly important because of the topic of materials dedicated to energy, and is one really of the hot topic for research in material science and trend of the future. So I think will be a subject everybody will be interested to listen the speakers. And I'm Plinio Innocenzi. I had to present myself from the University of Sassari. And let me give just my greetings to enjoy the conference and the session. This is the view actually from my laboratory. I'm so lucky to work here, and you are all invited to visit me and my laboratory anytime. And now let me give the floor. Sorry, there was I just given the floor to the next speaker, which is Dr. Piero Torelli from CNR Trieste.
Ladies and gentlemen, good morning. My name is Piero Torelli, and I'm a researcher at the IOM Institute of the CNR. I will give a talk today which regards ambient pressure soft X-ray absorption spectroscopy and its application in heterogeneous analysis. I would like first to thank the organizer for inviting me at this beautiful conference, who's giving me the possibility to show you the results of our last years of efforts and studies. During this talk, I will try to explain what is soft ambient pressure, soft X-absorption spectroscopy, and why it's important. I would start by saying that nowadays I'm convinced that everyone in the chemistry community is convinced of the importance and relevance of the operando spectroscopy that has known a huge development in the last 30 years, mainly in synchrotron radiation facilities, but also in laboratories. For example, I think to UV visible spectroscopy in operando conditions, and that nowadays those techniques are become a fundamental tool to investigate and to characterize the chemistry of the catalyst. Okay, so if this is a common basis, it's true also that those techniques has known a very different actually development in time. In particular, I have put it here 3, let's say, sister techniques, which are near ambient pressure XPS, ambient pressure XAS and IXAFS in the hard X-ray regime, and ambient pressure XAS in the soft X-ray regime. I call them sister techniques because they give quite similar information on the chemistry of your materials, and all 3 have known a very huge development in the last years. But near ambient pressure XPS, it's quite popular nowadays, and at least there is one beamline for each synchrotron radiation facility in the world that present one of the experiments dedicated to the techniques. Even more popular and is the ambient pressure absorption spectroscopy and EXAFs in the hard X-ray regime, and I would say that more than one beamline for each synchrotron radiation facility are dedicated to this kind of experiment, while setups dedicated to soft X-ray absorption at ambient pressure, there are only few in the world. I counted 3 for sure. Maybe I've missed someone, but this is the order of magnitude. So there is a huge imbalance between actually those techniques that, in my opinion, is absolutely not justified, and I will try to show you why. I have put it here, for example, the comparison of titanium edges from titanium silicalites, an experiment that we performed in collaboration with a group of University of Torino, of Silvia Bordiga, Elena Groppo, and Matteo Signorile, in which we have made a comparison between some defective and what we call perfect titanium silicalites. I will absolutely not enter into the details of the experiment, which is described in this paper, but it's just to show you.
Oh, ciao Valentina.
The hard X-ray regime of titanium present a very small difference.
Ha finito questo, presento Paolucci. Ok.
Chemical state of the samples, while the soft X-ray present bigger differences. And this is due to the superior sensitivity to the electronic structure of the soft X-ray absorption spectroscopy, together with the superior surface sensitivity of the soft X-ray absorption spectroscopy. So these are 2 reasons that, in my opinion, qualify the soft X-ray absorption spectroscopy as a very useful tool for the characterization of the catalyst. But still, this has been not completely received by our community. Okay, the good news is that all I will present in this talk is present at the high energy beamline of the electrosynchrotron radiation facility. Here, a top view of the beamline. This means that is available to you and to your group for your experiment. There are 2 public channels for access to this beamline, to this instrument. One is Electra. You can put a proposal at Electra, or you can put a proposal at NFFA Trieste, which is a new multi-technic facility, which is described here at this website. So there are 2 ways to access to this experiment. What is this experiment? Okay, conceptually speaking, this experiment is very simple. We realized a simple chemical reactor. We have a pipe for a gas inlet here. We have the space for a sample, which is represented by a green rectangle here. This is an heater that we use to heat the sample to the temperature of activation of the reaction, and the volume filled of gas at ambient pressure that is near the surface of your catalyst is separated by the UHV of the beamline by a silicon membrane put here, which is only 100 nanometer thick. So this permits to separate the vacuum of the beamline from the ambient pressure of the sample, but permit also to the X-ray to pass through. So permit us to record the X-ray spectra of the catalyst during the reaction. This is described in a review of scientific instrument of a couple of years ago. We added to this system a micro gas chromatograph, and for the analysis of the product of the reaction that happens while we are performing X-ray spectra. This is a typical diagram of a gas chromatograph, in which we can see the peak corresponding to hydrogen, oxygen, nitrogen, some of the most common gases. And this is useful because it permits us to correlate the spectra that we obtain from our catalyst to the step of the reaction. When the catalyst, when the reaction is still not activated, when the reaction is in a full speed, when we are at some particular step of the reaction, etc. So let's pass now to some practical example of experiment with this instrument. Here I show one of the first measurements that we performed with this instrument. which was from a cobalt oxide in a spinel structure prepared by PLD on a silicon substrate. It was a kind of continuous film, but granular, with nanoparticles of average size of 5 nanometer of diameter. And this sample has been loaded inside our reactor cell, and we recorded the cobalt L3 edges, L3 absorption edges, in different conditions. Let's see here, this black curve is the typical cobalt oxide in the spinel structure absorption edges that we record at room temperature at helium. Afterwards, we start sending hydrogen and we rise the temperature and we follow the absorption edges of cobalt. What we have observed? We have observed that as a function of temperature, the cobalt line changes and transform it into the red one that we have collected at about 300 Celsius that correspond perfectly to the cobalt monoxide, so cobalt oxide in the rock salt structure. Afterwards, we have switched off the hydrogen flux and we have put the oxygen in the gas line, and we have recovered almost perfectly the spinel structure that we have got at the beginning. So this was a very simple experiment that was meant to show you that we can follow a simple redox process of a cobalt oxide with XIS spectroscopy. Okay, this slide is just for showing you that to interpret the spectra, we have two main ways. One is literature. Cobalt oxide in spinel and in rock salt structure has very well-known spectra, so we know from literature what our spectra corresponds. But in case that the literature is not perfect, we can perform simulation, of course, as a function of the atom oxidation states, of the symmetry, tetrahedral, octahedral, and of course also of the spin state. Okay, so let's apply now these techniques to a, let's say, true scientific case, which is represented from an experiment we performed in collaboration with Paolo Ghigna of the University of Pavia, and what was concerning the carbon monoxide oxidation from an high entropy oxide. In this case, it was a combination of magnesium, cobalt, nickel, copper, and zinc with the same quantity mixed in a rock salt structure. This compound has shown in the last year a quite good activity toward the conversion of carbon monoxide into carbon dioxide. You can see here the diagram of the conversion of the CO oxidation as a function of temperature. We see that it activates the CO oxidation at 150 Celsius roughly, and at about 250 Celsius, it reaches almost 100% of conversion. Okay, but what is the mechanism behind this, this reaction? We have applied our system, we loaded the high entropy oxide into our cell, and we have acquired spectra for all the elements of the high entropy oxide at different conditions. In helium at 100 Celsius, at 250 Celsius in presence of carbon monoxide and oxygen, or simply in oxygen, or simply in presence of carbon monoxide. And what we have observed here, I present the cobalt and nickel absorption edges. Actually, you can see that somehow unexpected way, cobalt and nickel does not change completely. There is absolutely no change in those different conditions. This means that nickel and cobalt are actually spectators of the reaction, do not participate to the catalysis of the CO conversion. The same applies to magnesium and zinc, but let's see what happens at the copper side. These are the L2-3 edges, absorption edges of copper, again in the same experimental condition. we see that we start from the pristine sample with a pure copper +2. This is the reference, and the red one is the reference of the copper +2. And that during the course of the reaction, there is a small peak which arises here, and that corresponds to copper +1. This is the reference of the this peak is almost completely reduced when we flux only oxygen, meaning that those side that was reduced to copper 1 can be reoxidized, and is enhanced when you put only carbon monoxide flux. This is an inset that shows the behavior of the copper +1 in these different conditions. So what does it mean? It means that actually in our system, almost all the components, all the elements are a spectator, and only copper really catalyzes the reaction. And how it does it? It does it creating a reduction couple from copper +2 to copper +1 that is formed when the CO molecules is absorbed on the surface, and so on a copper side of our catalyst, that is then removed by an oxygen molecule that reoxidizes the copper to copper +2. Okay, I'm a bit late, so I will go fast on the conclusions. I hope that I was clear in explaining how this experiment works, and that I was convincing in showing that this kind of measurement is useful and carry a lot of useful information on the catalytic behavior of catalysts. And I will pass to make the acknowledgements. I would like to acknowledge the contribution of all the people who works on the API Energy beamline, and in particular Silvia Mauri, which makes the PhD in our group, and that this afternoon will present an experiment on the methane to methanol conversion studied using our ambient pressure soft X-ray absorption spectroscopy instrument. I would like also to thank Paolo Ghigna from University of Pavia, Paola D'Angelo from the University of La Sapienza, Valentina Colombo of the Milano University, and the large group of the University of Torino, which is listed here, with which we collaborate since several years now. I would like also to acknowledge the financial contribution of the NFFA project and the Moscato Prix. And of course, I would like to thank you for your attention.
Many thanks, Dr. Torelli. Really enjoy your talk, and I think the technique that you have shown is open plenty of opportunities for the analysis of materials. Maybe later I will contact you because it's so much interesting. And I ask if anybody has a specific question for Dr. Torelli to ask about his presentation. Okay, let's thank again Dr. Torelli. It was really interesting talk, and thanks for a presentation.
You're welcome. Thanks to you.
Thank you so much. Really enjoyed. And let me introduce the next speaker is Professor Paolucci from University of Bologna. Welcome. And he will talk about carbon-based hierarchical nanostructure for the electrocatalysis. Professor Paolucci, please.
Okay. Good morning, everybody. I hope everything is fine. Is it okay? Yes.
Yes, it's fine. It's fine.
First of all, I would like to thank the organizer. Okay, thanks. I'd like to thank Antonio Politano for inviting me to give this lecture. I think this is a very interesting meeting, and I'm very sorry about that. So, be using my time to show you some of the activity we have been performing in the field of electrocatalysis for over the last 10, 15 years. When you talk about electrocatalytic systems, what you have to be sure is that the right choice is made about the support, the substrate, the electrode material that you are using. Not only the electrocatalytic, not only the catalytic part of the system is important, but also how you couple it to the electronic device that you're using to promote electrocatalysis. And what you have to be sure, first of all, is that mass and charge transport won't limit the catalytic efficiency of the system. So you need to be sure that continuous access to the catalytic side by, on one side, charges, and on the other side, molecules and ions is maximized. Also important is the stability, and so mechanical, electrochemical, and chemical stability must be must be granted. And especially when you consider that most of this process takes place under conditions that correspond to high polarization levels, extreme pH, sometimes bubble formation, the temperature gradients, everything can decrease a lot the durability and the lifetime of your system. And in this context, we and many groups around the world have found that using carbon nanostructures is a good choice. And the reason for that is that, first of all, all these materials usually have a very high chemical stability. Further, this is important, you know also that there are many different chemical approaches to functionalize this carbon nanostructure and the carbon materials in general. And they have, especially in the case of two-dimensional, one-dimensional system, high aspect ratio and specific surface area, which is important because the electrocatalytic properties are properties that depends on the extension. These are extensive properties of the system. And last but not least, as we can say, all these systems have very interesting electronic properties. In some cases, are granted by the delocalized pi electrons properties systems that they have, like in the case of two-dimensional, one-dimensional systems. And this gives the materials a very rich, unique electronic property and very rich photophysical and redox activity, which is important for electrocatalytic applications. Examples will be shortly talking about this system we have been working on are based on graphene, for instance. And graphene can be relatively easily functionalized. In this case, we might say decorated by using metal particles, in this case, platinum nanoparticles, by chemical or electrochemical approaches, systems. They may also be modified using a covalent approach, covalent chemistry. So attaching the catalytic system onto the electrodes, onto the nanocarbon material using chemical bonds, like in this example here. Other examples I will be taking from the field of micrographites. We may say micrographites are small crystals of graphite, of course, and this may be, we may say, catalytic properties may be attached to micrographites using different approaches, like, for instance, direct inclusion, as in this example taken from the literature, or in these other examples where different approaches that was developed by some colleagues of ours in Bordeaux based on the so-called graphenides that are heavily negatively charged, highly reduced graphene sheets are used to decorate with metal nanoparticles the surface, and so obtaining interesting electrocatalytic properties. Also, carbon nanotubes have been used. One example that's historical importance for us, because it was one of the first on which we worked, one of the first electrocatalytic systems on which we worked, is where based on the covalent approach, so covalently bonding the catalytic site onto the carbon nanotube material. Or other example like this one, in which the catalytic site, in this case palladium nanoparticles, were embedded and attached onto the carbon nanotube surface by using a core shell approach. Last but not least, boron diamond. I won't have time to talk about this, but also these are interesting systems. Boron diamond is not intrinsically a carbon nanostructure because it is a three-dimensional structure, but still can be used, for instance, to obtain this interesting core shell system that is very efficient towards CO2 reduction. But I won't have time to talk about this, unfortunately. So I will start giving you a few more details about the system I mentioned. This, as I told you, is an importance for us, an historical importance for us, and we started working on this when the group, in collaboration with the Marcella Bonchio's group in Padua and Maurizio Prato's group in Trieste, when the group in Padua discovered this new catalyst that was very, very efficient towards water splitting reaction, so oxygen evolution reaction. And this was very efficient and also very stable. The stability came probably by the fact that you have this active ruthenium-oxo cluster that is embedded between two hemicaps of polymetallic material that gives the whole system a very high stability. So the next step was, the idea was to transfer this very high efficiency from solution to the electrode, so to obtain a heterogeneous electrocatalytic system. And the idea was, where Maurizio Pratos came in the story, to use carbon nanotubes. And the idea was to exploit the fact that polyoxymetallic groups are very highly negatively charged polyanionic material, and introducing polycationic dendrons, so covalently linked groups onto the outer tube of the multi-wall carbon nanotube, which with a large number of positive charges. So exploiting electrostatics to obtain a hybrid system. And this was done and proved to be very stable in aqueous solution. The hybrid system was very stable in aqueous solutions. And at the same time, since you have a monolayer, basically, of the catalytic site around the nanotube, you also have a very easy access to the catalytic sites from by the water molecules. And at the same time, you may obtain very high loading. So taking use and exploiting this material, we transformed our electrosubstrate ITO material that is not at all efficient towards oxygen evolution reaction. We transform this in a very strong and very efficient electrocatalytic system. And because the nanotube gives, through the connection with the electrode, gives a very good way to disperse the positive charge that is released by the water molecules during the oxidation onto the electrode surface through a very efficient electrical wiring. And these are the results, just briefly. The results that you obtain when you measure the turnover number and turnover frequencies of these systems once it is attached onto the electrode surface and deposited onto the electrode surface, and you see that at a relatively not so high over potentials, you obtain the turnover frequencies that are almost the same as in water in aqueous solution. So in the homogeneous system, that is the most that you may obtain from this catalytic material. So this was a first example where coupling the catalytic material with a nanotube, with a carbon nanostructure, could give very interesting properties. Second example, I will be showing this where the catalytic sites that are palladium nanoparticles are embedded within a core shell system onto carbon nanotubes. This was developed in collaboration with Paolo Fornasiero. I'm not sure if Paolo will be talking about this during his talk this afternoon, but I will give you only a few details about the synthetic part of the story. The idea was that what we wanted was a catalytic that could promote hydrogen evolution reaction in a specific range of pH where most of the catalytic systems are not so efficient. And this is something that you usually observe. This deviation from the thermodynamic expectations in the range between around 4.5 and 9.5 pH is associated to the fact that this reaction, the water dissociation reaction, is very slow in this range of pH, and so the availability of protons is low, and this explains why we have this deviation. So the idea was to develop a catalytic system, in particular an electrocatalytic system, that could work also in that region. And so the choice, the hybrid system that was developed was based on the choice of 3 different components, each of them with a very specific and important role. Palladium, first of all, the palladium nanoparticles, because as we know, it's almost at the top of the volcano plot, so you may obtain good efficiency with low loadings. Multi-wall carbon tubes to provide the structural scaffold, similar to what we did with our previous system, and also managing the electrical wire. And titanium dioxide, the shell, that had the role to stabilize the nanoparticles and prevent them from reorganization or reconstruction during the process. But in fact, in our studies, we found out that the titanium dioxide is also playing another important role in the system. All the 3 components, in fact, are very important. And this is, as I was saying, this the synthetic approach. Paolo developed these 2 different approaches, 2 different synthetic routes to obtain the final material. In one case, the core shell system can be deposited onto the nanotube, but you need to have some template groups onto the nanotube surface. And these template groups are these carboxylic groups that may be introduced by either thermal treatment and in the presence of a strong oxidant. You may introduce these carboxylic groups directly linked onto the tube. In the other case, they exploited the radical chemistry, and using the so-called Tour reaction, they introduced these benzoic groups onto the surface. And in both cases, you may then template the formation of the core shell system around the nanotube. So these are the 2 systems, and you see that in both cases, the final material will still contain this carboxylic groups. These are organic material in between the nanotube and the core shell system. And this is important because this has a role as expected on, as an effect as expected on the properties, on the electrocatalytic properties that are shown in this picture. So the catalytic activity of the core shell nanoparticles were strongly enhanced by the presence of multi-wall nanotubes. This is the result. So the turnover number as a function of their potential in the case of the layer of the core shell nanoparticles, so palladium with a titanium dioxide shell. And these are the results that we obtain. The other 2, the black and the red lines, are the results that we obtain with the system where multi-wall nanotubes is introduced. If you just just compare the 3 different systems by using the so-called turnover frequency node, that is the turnover frequency extrapolated values at 0 over potential, you see that you have an increase by 1 order of magnitude passing from one system to the next. And interestingly, when we calcinated the material, so we remove the carboxylic groups, the 2 materials give us a new material with a completely much higher activity, and the same for both. That is expected if you consider that you are removing the carboxylic material and the organic material, and you have a better efficiency because you have a very better coupling, electronic coupling between the carbon nanotubes and the core shell system. And this is the picture of what you have. In fact, after calcination, the palladium nanoparticles are decorating, are located and onto the multi-wall carbon nanotubes, so directly coupled electronically to the multi-wall carbon nanotubes, and the titanium dioxide layer. This is a picture when it is partially detached to show what is behind and underneath, and is protecting the overall system. But it's the titanium dioxide material is not only playing a protecting layer role. And what we observed by investigating the electronic properties of the titanium dioxide in the system by using the Motte-Schottky plot approach is that the properties of the titanium dioxide is modified by the presence of multi-wall carbon tubes. In these three different systems, we have a different percentage of multi-wall carbon tubes with respect to titanium dioxide. It is increasing this direction. And you see that while you have almost the same flat band potential as expected, because titanium dioxide is the same in all systems, both the doping levels and the surface state density increases when you increase the multi-wall carbon tubes content in the average system. And in particular, the titanium dioxide becomes more electronically conducting because you increase the density, the doping levels, but at the same time you also have an increase of the surface state density. And we identified this defect in titanium dioxide as oxygen vacancies in titanium dioxide. So the titanium dioxide is playing another role in the system that is shown in this picture. Titanium dioxide may be coupled, may be attached onto the titanium dioxide. The vacancies may be coordinated by these titanium dioxide atoms onto the titanium dioxide surface. And because of that, you may have a promotion of the water dissociation. So increasing locally the concentration of protons with respect to the bulk that may make the whole process more efficient. This is the interpretation we made of our results. And I will pass very briefly to another system. I won't talk about this, but using the same approach, Paolo and Maurizio developed noble metal-free electrocatalyst useful for the CO2 reduction. I won't be talking about this because Miriam, our PhD student, will be talking about this tomorrow. And so I invite you to to attend her presentation where she will be talking about this. And I will move now to the last system I will be showing, and it is based on a completely different approach, different materials, starting materials. In this case, we are using graphite, micrographites in particular. And this approach was developed by Ferdinand and Alain at CNRS in Bordeaux. It is based on graphite intercalation compounds, where you intercalate protons, and then using THF, a specific solvent where this material is stable, you may, using sonication, you may obtain stable graphenite solutions. Graphenite is, as I was telling you before, is the term that we use to describe a graphene layer or single layer or two layer, more or less, graphene layers, which are heavily negatively charged by reduction. So with potassium, we reduce them, and after dissipation, you obtain this kind of polyelectrolyte in solution. And these are very good for promoting reduction process because they are kind of floating electrodes, negatively charged, where iron, for instance, in this case, iron ions can be reduced, forming spontaneously this decorated graphene with the iron nanoparticles on it. Then, when you expose it to light, to air, it will form iron oxide. In fact, the material we have been investigating were in fact iron oxide nanoparticles onto decorating graphene layer. And very briefly, the interesting results that we obtained in this case are related to the fact that using that approach, they found out that it's possible to control very efficiently the size and distribution size distribution of the nanoparticles onto the graphene layer by just selecting the size of the graphene layers themselves, because this will give you different charge density, and with different charge density you have different kinetics of the iron deposition process. And so this has an effect on the size of the nanoparticles onto the graphene layer, but also on the electrocatalytic efficiency. So this material were drop cast onto the electrosurface, and these are the summary of the result that we obtained with the three different sizes, so small, medium, and large. you see. And you see, the more you have a best results. And what it is interesting, this catalyst that we chose in this case, you have a bifunctional material that is able to promote both the reduction and the oxidation of the oxygen reduction, and with values for the output potential that is comparable, in some cases better than those that are in the literature. So with this, I finish. I stop my presentation. I would like to acknowledge the contribution from all the groups we have been collaborating with for so many years that have been already mentioned during the presentation, and my colleagues and collaborators in Bologna, in particular Giovanni Valenti, the guy smiling here, Miriam Mora, who will be talking about tomorrow, Meng, our former PhD student who worked on part of this story, and Enrico Verlato at the National Research Council in Padua. And I wish to thank all of you for the very, very kind attention.
Dear Professor Paolucci, thank you so much. Very, very impressive presentation, and enjoy a lot. I have just a small question for you, and how you can control the dimension of graphenite, and to which extent you can control? You have single two layers, but also you can control shape, dimension of the graphenite.
Yeah, this is not difficult because you start with micrographites, and you may obtain micrographites and control easily the starting materials, size distribution. And then this material is not strongly affected by the intercalation procedure. So the size of the graphene layers that you obtain finally are almost the same as the micrographites you start with.
Okay. Many thanks. Please, if anybody has any other question for Professor Paolucci. Please don't be shy. Professor Paolucci will be very happy to reply to your questions, I'm sure. And Professor Paolucci, no questions. So thanks so much again for your presentation.
Thank you.
And
Thank you very much.
Thank you
very much.
And let me introduce the next speaker, which is Professor Lixue Zhang, Qingdao Daxue. Professor Zhang, ni hao, I give you the floor for the presentation.
Good morning, I'm Lixue Zhang, come from Qingdao University, China. First of all, I would like to thank Professor Antonio Politano and Professor Plinio Innocenzi for giving me this great opportunity to join this great New Times conference and report some of our recent works on defect engineering of cobalt-based nanostructured electrocatalysts. Here is the outlines. I will introduce background firstly. As we know, exploring high-efficiency new energy conversion technology, such as electrochemical water splitting and metal-air batteries, is of great importance for the development of human society. For these electrode reactions, including oxygen evolution reaction, hydrogen evolution reaction, and oxygen reduction reaction, their catalytics are usually slow, and thus electrocatalysts are needed to decrease the overpotentials and to improve the energy efficiencies. For example, oxygen evolution reaction, OER, is a proton-coupled 4-electron transfer reaction. Its catalytics is quite sluggish. Presently, ruthenium oxides and iridium oxides are the most efficient catalysts for OER, but the scalable applications are hindered by the scarcity, high cost, and unsatisfactory durability. Therefore, searching for earth-abundant, non-precious electrocatalysts to replace noble metal catalysts is highly imperative for developing electrochemical energy conversion devices. Cobalt element has unsaturated d electron orbit, multivalent states, high coordination number. These properties make it very promising in electrocatalysis. Now, cobalt-based materials are widely used as homogeneous and heterogeneous electrocatalysts. As a very common cobalt-based compound, cobalt oxides have been broadly exploited as OER catalysts due to the certain catalytic activity, low cost, and electrochemical stability. However, its performance is still not high. It has been demonstrated that nanostructure fabrication, composition adjustment, and crystal plane control, and oxygen vacancy construction can enhance its catalytic activity of cobalt oxide. Anyway, the low intrinsic catalytic activity, poor conductivity, and limited active size of conventional transition metal electrocatalysts still impeded their practical applications. As we know, the defects, including vacancy defects, doping defects, and interstitial defects, can modify the surface interface structures of the materials, and then it can modulate the electrocatalytic behaviors, which has been recently demonstrated by some groups. Thus, we proposed our research strategy is that controllably constructing defects into cobalt oxides to improve their intrinsic catalytic activity. Next, I will introduce our work in nitrogen-doped cobalt oxide, nitrogen-doped carbon as bifunctional oxygen electrocatalysts. Despite some new designs have been reported on heteroatom-doped cobalt oxides for electrocatalytic applications, it is still a great challenge to synthesize defect-engineered cobalt oxide nanocarbon hybrid electrocatalysts with controllable nitrogen doping, tunable electronic structure, and well-defined morphology. In addition, the role of nitrogen dopants in cobalt oxide, especially the effects of nitrogen doping on the atomic structure and the surface electron states around metal sites, still remains ambiguous and needs in-depth interpretation. Here, we report a new defect-rich nitrogen-doped cobalt oxide nanoparticles, nitrogen-doped carbon framework, strongly coupled porous nanocubes, derived from continuous heating the ZIF-67 precursor in argon, air, and ammonia. The nitrogen-doped cobalt oxide nanoparticles are homogeneously embedded in the nitrogen-doped carbon. We can see that the distribution of cobalt, oxygen, and nitrogen elements in the sample are very uniform. Electrocatalytic capability of the as-prepared nitrogen-doped cobalt oxide electrode towards OER was evaluated by linear sweep voltammetry. The nitrogen-doped cobalt oxide samples show dramatically enhanced performance compared with pristine cobalt oxide and is comparable with the commercial ruthenium oxide catalysts. To drive a current density of 10 milliampere per centimeter, an overall potential of only 266 millivolts is needed. It also possesses a small Tafel slope, remarkably lower than those of pristine cobalt oxide and ruthenium oxide, indicating the favorable kinetics for OER on nitrogen-doped cobalt oxide. The electrochemical durability and stability of the prepared nitrogen-doped cobalt oxide catalysts are also very good. To investigate the composition and chemical valence of cobalt oxide and nitrogen-doped cobalt oxide samples, XPS, ZAFs, and ESR tests were performed. We can find that the introduction of nitrogen atoms can optimize the electronic structure of cobalt species, leading to the increased electron density of cobalt species and the formation of cobalt-nitrogen bonds. There is no obvious change in the crystal form of the catalyst after nitrogen doping, but the coordination environment of cobalt atoms changed, and the cobalt-oxygen coordination number decreases. The nitrogen doping also leads to the formation of abundant oxygen vacancies, which contributes to the formation of new active sites and the improvement of the conductivity. To further investigate and understand the enhanced OER performance of the as-prepared nitrogen-doped cobalt oxide fundamentally, the adsorption gives free energy on the cobalt oxide and the nitrogen-doped cobalt oxide lattice were investigated by density functional theory calculations. We can find that after nitrogen doping, the potential determining step changed from the formation of adsorbed oxygen step on cobalt oxide to the formation of OOH step on nitrogen-doped cobalt oxide. And the theoretical over potential decreased to 0.41 fold from 0.64 fold, which is well agreement with the experimental results. In addition, after nitrogen doping, we can find that the band gap decreased to 0.58 e-fold from 1.63 e-fold. The increased conductivity is also very important to the electrocatalytic activity. The stability of the catalyst is, of course, very important. We can see that after long-term anodic electrolysis, the catalyst preserves its nanocubes feature and crystalline structure. The decreased electron density around the cobalt species, indicating partial surface oxidation of nitrogen-doped cobalt oxide during the OER process. However, we can still find the existence of cobalt-nitrogen bond confirms its stability. Overall, the OER catalytic performance of the nitrogen-doped cobalt oxide catalyst compares favorably to many recently reported transition metal-based OER catalysts. Remarkably, the prepared nitrogen-doped cobalt oxide samples also exhibits high ORR activity and stability, which is close to PET catalysts. Thus, the nitrogen-doped cobalt oxide electrocatalysts can effectively catalyze both the OER and ORR. It's worth noting that the influence of the nitrogen doping amounts on ORR activity is not very apparent, which indicates that the improvement of ORR activities for nitrogen-doped cobalt oxide catalysts may be mainly due to the enhancement of electrical conductivity by nitrogen doping. Considering the bifunctional oxygen electrocatalysis of the prepared nitrogen-doped cobalt oxide catalysts, a zinc-air battery was fabricated using nitrogen-doped cobalt oxide materials as the oxygen catalysts. The assembled battery shows better power density and cycling stability than the battery using normal metal catalysts, indicating the potential application of nitrogen-doped cobalt oxide in metal-air battery. Compared with nitrogen, however, phosphorus has a larger atomic size and a higher electron donating ability, making it an intriguing dopant candidate to enhance the electrochemical performance by modulating the electronic structure of the cobalt oxide. However, less attention has been paid to develop phosphorus-doped cobalt oxide electrocatalysts. Herein, we demonstrated that phosphorus-doped cobalt oxide nanowire array on nickel form can be fastly derived from cobalt oxide via low temperature annealing using this material as a phosphorus source. As known, nanoarray structure can facilitate the diffusion of electrolytes and expose more active sites. The morphology and phase of cobalt oxide did not change significantly after phosphorus doping, and XPS results confirm the existence of phosphorus-cobalt bond. That means phosphorus atoms have been successfully doped into the crystal lattice of cobalt oxide and replaced parts of the lattice oxygen atoms. Such phosphorus-doped cobalt oxide shows more remarkable OER and HER activity than pristine cobalt oxide in alkaline solution. And the voltage of electrolytic water decomposition by using phosphorus-doped cobalt oxide as both anode and cathode is only 1.63-fold. And this catalyst also has a good long-time stability. To sum up, first, new methods for constructing heterodoping defects into cobalt oxide have been proposed. Second, the doping defects can adjust the arrangement of surface atoms, optimize the electronic structure of cobalt, improve the adsorption behavior of reaction intermediates, and enhance the conductivity of cobalt oxide. Third, surface heteroatom doping can bring about significant catalytic activity improvement for transition metal-based electrocatalysts, and such a strategy holds great potential in electrochemical volt splitting and metal air batteries. Thanks for the support from fundings, and thanks to my students Mr. Chao Wang and my collaborators. Thanks for your attention, and welcome to Qingdao.
Dear Professor Zhang, thank you so much for your presentation. Sincerely, I have been to Qingdao many times. It's a place I love so much. It's a beautiful city. And also, I came to your university a couple of times. So really, I hope that when will be over, we can meet in Qingdao, your beautiful city. And maybe you can come here, also a very nice place. So thank you.
Okay.
I really enjoy your presentation. Very interesting, also because it's a hot topic, developing advanced batteries. And let me ask if there is any question for you. If some of the listeners here, participants, have any question. Or otherwise, just a small question from my side, because you doped with phosphorus. Do you have in mind any other possible doping elements to test for your battery?
Because in our lab we have doping nitrogen, phosphorus, and sulfur. Yeah, we also perform experiments about the sulfur doping, and in addition, we also want to perform some experiments about the fluorine doping, but we found maybe it's not so easy, so we drop it. Because the heteroatom doping can modulate the electronic structures of the transition metal side, so it can influence the electrocatalytic activities. We have many other experiments also confirm this point.
Yeah, you have a lot of job to do, a lot of work to do.
Yeah. Yes.
Okay. If there is other question, let me thank so much, Professor Zhang. You was very kind to participate, to attend this event. Really deeply my thank. Really appreciate your participation. It was a very nice presentation, very important. So thanks so much again.
Thank you. Thank you, and welcome you to Qingdao again.
I hope soon, Professor Zhang. Really, I hope soon. I lost so much, I visited the Qingdao factory so many times of beer.
Okay, so see you in Qingdao.
Yes, keep a beer for me. Okay,
Yeah.
let's move to the next speaker, Dr. Samson from CNR, and she will present, she will talk about perovskite, a unique versatile structure for energy application. Please, Dr. Samson, you can start your presentation. Thank you so much.
Okay, thank you very much. I hope you can see my screen and my presentation.
Yes, it's very good. Perfect.
Thank you very much. So first of all, thank you, Professor Innocenti, and thank you all the scientific committee for giving me the possibility to present my work, the work of my group on perovskite. I'm a researcher of the National Research Council and the Institute of Science and Technology for Ceramics in France. Just give me some moments to address a problem that we all know about at the moment. It is very well known. It's very it's a common problem. We will hear a lot during this conference about the problem linked to the greenhouse gases and conversion, but I only wanted to stress that the emission of greenhouses and the greenhouses is not only giving a direct global warming effect, but also induce a lot of different other effects that are going to deeply affect our lives. So it's very important to address in a most coherent and global way this problem of the emission of greenhouse gases. Obviously, the first thing is to switch from renewables. Renewables obviously are linked to the replacement of the fossil fuel, and on this side, obviously solar energy system is the one that we are looking more in depth for its availability. We are always looking at solar conversion as photovoltaics, so direct conversion of the sunlight into electricity, but actually the sun offers us a lot of different opportunity to exploit this energy source as directly to electricity, as we say, with the photovoltaics, but also looking at a directly way of using it that is also a way of reducing in such a way the gas emission, like using it to convert the CO2 or other gas emission towards chemicals and materials. This is really something that we have to look into more details in the future. It's something that has been on for a lot of time, but now I think it's time for pushing up, and there is a lot of very interesting talk also in this conference about that. Obviously, when you're looking at the reduction of CO2, specifically, we can look at the nature with the photosynthesis, and so looking at directly convert carbon dioxide with a catalyst in a photochemical approach, or considering the asymmetry and high energy of the C-double-O bond using an external bias and a catalyst in a photoelectrochemical process, so in a PEC cell. Obviously, in all these approaches, it's important not only to look at efficiency in the materials, but also to a stable one. Because if we want to push forward this kind of approach, we need something that is more stable during this long time. So it's a kind of trade-off between efficiency and materials stability. And that came to my perovskite. Perovskite is a very old material. It's based in name from the mineral that you see here with a very nice cubes of titanium calcium, calcium titanate, in which you have basically a common formula AbX3, basically, when you have the B cation on an octahedral and a side cation that is a bigger one, generally speaking, on a center cubic. This is basically governed by the so-called tolerance factor, so the ratio between the cation and the anion radius are going to give you the kind of structure that you are going to have, because it's a very, very unique structure in this sense. As much as you're working with it, you can play around with it very nicely, doping and replacing the A side, the B side, or the X side as well. And as much as you're playing around, the structure is going to react or either contracting or expanding the cell, or also with octahedral tilts, so changing the direction. But we have also some kind of polar distortion, especially in the B side. And this is well known because perovskite are the most common material used, for example, for ferroelectric and piezoelectric activities. Perovskite that are mainly known for the oxide part. They are very subtle and very unique material with their functional activities. When you are looking at the solar conversion, all this kind of substitution that you can do or distortion of the cell are going to affect what is the Bx or B length of the bond or the angle between these atoms, and these are going to change particularly the spectral properties of the compound. We are probably all aware of the fact that perovskite are now considered the holy grail of photovoltaics application, where the A side is an organic part actually. So the most common oxide part is replaced by a different kind of organic quartz coming from methyl ammonium to the imidazolinium one, and this is pushed, as we probably know, the conversion efficiency of the photovoltaic cells from the very beginning to the actual record cell that you can probably see here. I think if you can see it very well, it's 25.5%. It's the record of the 2021. This is the updated NRL chart on best research cells efficiency, and you can see here how this is progressed very steadily from the discovery of the compounds towards the actual results. So now it's very, very well-known materials that offers a lot of different possibilities and opportunities. But we all probably know that there is still some issue to solve on the perovskite organic base, organic perovskite, especially the humidity and the instability of the system over humidity that is going to destroy the structure actually, especially acting on the organic parts. And that is for the reason why the organic part is started to work on be substituted with the inorganic part, going towards what is called the all inorganic perovskites. One of the most common compounds used for this use is cerium lead bromide. This is a compound that is known also for its electroluminescent properties, and we had a look if we could use also to CO2 conversion. So we made a very nice, very simple oleate synthesis, very low temperature actually, for this kind of system. We obtain a very nice morphology of a system with particles of nanometric one. The phase a pure monoclinic one, and the band gap is suitable for this kind of application. This is not very surprising, as we know that the system is worth for that. But what we were looking at now was to use it directly on converting CO2, and the first step of this kind of system is to see with the target molecule, generally is rhodanine B in water, if the system is able to degrade these compounds. And what we found that, yes, there is a kind of possibility in doing that, but what happened in the end is that the bright yellow materials is turning completely white. And this is because there is a conversion of the cell induced by water, as we supposed, that is changed from a nice, very ordered perovskite cubic structures to a different, very different one that you can see here, the formula, and obviously changing and affect the degradation ability. The system is still able to degrade a little bit, but actually is not stable anymore. So it's not something that you can definitely use. And to check this, we found, and we try to do the same in ethyl acetate solution. This is a common solution used for soil conversion, as there is the possibility to dissolve quite a lot of CO2 in solution in this kind of system. And actually what we see that the system is working nicely in this time on the degradation. We obtain basically a complete degradation of the system in ethyl acetate, and the system is retained its complete structure. So water is an issue. We knew it. We thought we could go around that. We are aware of this, and we would wanted to check this, and the effect of ethyl acetate is probably due to its effect of all scavenger that is able to block the recombination between all electronic charges around the system. So we anyway go through working through having a PC system, so a photoelectrochemical cell produced and filled by spin coating in full wind. The system, the film, as you can see, is quite nice. It's very uniform without cracks, and the phase is retained. But as we know about the water instability, you can see here the effect when you look at the system deposited on an FTO glass living in water for not a long time, actually. So what we tried to do was to protect the film. Actually, we tried with organic part, but this is not very effective because it's true, it's helping in protecting the system by water interaction, but then the tails of the organic part is going to affect the conversion ability of the system. So this is not actually an option that we think is worthwhile pursuing. So we choose another approach that was with protecting the film with two different coatings, one of platinum and one of carbon. And as you can see, the system is retaining basically the morphology. The morphology is a little bit different, obviously, because platinum and carbon has different aspects on the top. We'll check the transmission of the system. The platinum one is going to affect, you can see here, the transmission of the glass from the side of the coating and the opposite side, where you can meet the glass and then the film. And the graphite one is definitely less, I would say, covering the system. The transmission is a little bit affecting from the platinum side. It's important to stress the thickness of the two coatings are the same, both with carbon and platinum, but obviously the microstructure is very different. So we check the water stability by cyclic voltammetry. You can see here clearly as the first cycle of the system is giving a certain kind of signal, and at the end we perform 30 cycles in ferrocyanide, copper ferrocyanide system. And you can see that at the end of the third cycle, the voltammetry plot is basically the one of FTO, the FTO glass. The system is actually changing a lot, very more stable for sure. When you have the two coatings, either with carbon and with platinum, we reach a good stability. Obviously, the voltammogram are a little bit different between these two systems, because on the carbon side, you have just the oxidation reduction of the iron cyanide. On the other side, you have also the small production of hydrogen induced by platinum as well. Then we look at the electrochemical properties of the two film. Not surprisingly, we have to use two different equivalent circuits for the impedance analysis spectra. This is basically due to the different effect and morphology of the system. And you can see here that we have different behavior or resistance between the two samples. Obviously, when you have a platinum effect, you have obviously more conductive elements. The film is more conductive in contact with the electrolyte, so the resistance is definitely less than on the other side. On overall, we have more or less the same total resistance basically of the system. And with the mode Schottky analysis, we look at the conduction behavior, and not surprisingly, the system, both the system and type semiconductor, with the valence band suitable for CO2 reduction. So we applied finally this film for photoelectrochemical in a photoelectrochemical cell that you can see here, the energetic plot that we built, starting from the valence band behavior and obviously the energy gap, is giving you the impression that we are able to reduce the CO2 into different compounds. And then we measure obviously the Faraday efficiency of the system. Obviously, this system still has some problem, but is able to reduce CO2 in oxalic acid in specific. We check it with gas chromatography and high performance liquid chromatography, and this was the only compound found, except in the case of platinum, where we have a small production of hydrogen as well, but this is expected as platinum is a good catalyst for hydrogen production. So the Faraday efficiency is quite nice, especially in terms of the system protected with carbon, with the carbon on top, with graphite, and the system is retaining basically its stability after the functional trials, even for definitely quite a long time, and even working at 0.8 or 0.5 volt. So this system is able to protect and is able to work better in this part, and we are going to make more work here, considering the other protecting layer to improve the property as well, of changing this some issues that are still present, especially the Faraday efficiency overall. But looking at this, we went back to the oxide-based perovskite, the cubic ADL3 aristotype. It's, as I said, it's the first type of perovskite that has been introduced, and is well known for different kind of application. Is very stable, and yes, the ability to, as I said before, to be doped or changed in a very easily way. So as I said before, you can play around with A side under bonding, for example, inducing octahedral rotation. And as I said before, every time you induce some changes in the link, in the bond, you are going to affect the energy band gap of the system, for example, just to say something. But there is another nice opportunity with this kind of material, is the layering. Whenever you are outside the tolerance factor value of 1, that is commonly considered the best one for the more common tolerance factor that is giving you a pure perovskite, then the system is going to change into different families of oxide, going through Radisson and Popper, Dion Jacobson, double perovskite, and RVVs. These are actually very well known different families of compound, especially known for their conductive properties, either electronic or ionic, or for the ferro or piezoelectric material properties. And this is important to bear in mind, because ferroelectric properties in a system can be very useful when you have to improve also the conversion photoelectric properties, because it's helping in reducing recombination, basically. And so we start looking at the double perovskite. Double perovskite of the formula that you see on top, commonly known as CCTO. You have a double A side when you have calcium or copper on it, and then you have the very nicely TO6 octahedra distorted, as you can see there on the structure. Is done by non-toxic element and is a favorite band gap. It's actually a very refractive material. It's very well known for dielectric properties, actually. But knowing that as a favorite band gap, we'll look into it if it was possible to use it for conversion activities. So we did two kinds of synthesis, a soldier one and a soldier combustion one. As you can see, the system is very refractive. Actually, the main point of the system is that it's not there is no clear indication that the pure phase can be obtained without doubts, even in literature up to date. And so you can see you have to go to very high temperature of synthesis, even if the synthesis is done by chemical methods, and the BAT consequently are very low, as you can see. So you have a surface area that is not very nice for this kind of photocatalytic application. We did still the rhodamin B approach of to check the possibility of the system to act in this sense. The system is active also in dark, so it's able to trigger the degradation anyway, but we have definitely improved on the light side, and you can see you can reach, even with a very low surface area, a very low, very high degradation side. So what we did is that we wanted to play around with structure C, even if the system is well enough. If we manage to include some other ion able to improve the conversion efficiency, we tried with iron in different composition actually, but as you can see, whenever you reduce the copper, actually, this is not okay, it's not very surprising. Copper is very well known for this kind of application, but whenever you are extracting copper from the structure, you have a reduced ability to photodegradation. So we play around again and we said, okay, let's have a look what happens if we consider a structure that has a doping of iron, or we remove completely part of the copper. So giving the composition that you see around, is it the copper really the key elements from this compound? And actually, actually we managed to obtain all the three phases. Again, we see that the surface area that we obtain is very low. if you are going to play around with the structure, you still have some small secondary phases that is not possible to avoid. We tried a lot of different mixture and condition synthesis, but actually they are still there. And as you can see, it's clearly again that if you take out the copper from the system, the degradation is going to going worse. So copper is really the key point in this kind of compound, even if the system is not changing a lot in terms of crystallographic cell. So looking at this, we realized obviously that the surface area was really low. So we tried to improve the properties, milling the power for a long time in high-energy planetary milling. And as you can see, we have a double effect actually. We improved the surface area as we planning to do. But what happened again is that we have pure phases. So this is a kind of mechanosynthesis approach, as you allow me to say that. So you improve with these high energy planetary mills also the formation of the phase. But what the nice thing that you obtain doing like that is not only that you increase the surface area, is not only that you have a pure phase, but you change also the energy gap. This is a system. This is an effect of changing actually again the role of copper inside, because the copper is changing its coordination, or is disposition in space. So it starts from a planar one, from an tetrahedral one disposition, and that is going to affect the energy band gap of the system. And as you can see down here, you clearly improve the properties of the degradation system in this way, and you reach the almost complete degradation with the parent compound. Obviously, we hope to have different effect with iron and copper, but obviously this is another way in which we can help in inducing more efficient doping on the system. We did with that the electrodes by screen printing this time. The system, as you can see, the film are nicely homogeneous. The thickness is a little bit higher than before. This is going to affect a little bit the system, but still was worthwhile in it. And we tried the electrochemical characterization of the system that we tested. As you can see, we have a nice redox capability of all the system compared to the FTO one, and a nice storage capability. The iron dope materials have an higher Faraday currents, probably due to the ability that it has to have a better redox capabilities with copper ferrocyanide, while the storage capability is a little bit higher for the defective compounds, probably for the defective part. We are still investigating that, but the intercalation of charges is probably the main effect in this kind of compound. We did not Shakti analysis on this system as well. They are still N-type semiconductor. The flat band is more or less similar for the system, except for the iron one that probably is more prone to electronic recombination. Finally, just a small, briefly noticing on the Aurelius series. So we start playing around also with layering. So looking for the series, this is going from the parent structure of the Aurelius compounds towards adding more perovskite block. Basically, as you can see in the Arabilis family, is formed from the common perovskite slab that are intercalated with bismuth oxide rock salt system. This system is known for its high dielectric constant, but also for its ferroelectric properties that we plan to use to improve the properties. And as you can clearly see, going from a completely layered compound to a perovskite one, you have a nicely changing in color and obviously on the energy band gap of the materials. We have still a lot of measurement doing on this system, so we are not there yet, but we still are playing around with the structure, aiming the possibility to tailor in a lot of different properties. So I hope with this talk to highlight the importance of perovskite for the energy conversion. Perovskite are very well-known material in the hydrogen economy for their electronic and ionic, either anionic or protonic conduction, but can be very, very useful also for the solar conversion part of the story. We can play around with the structure very nicely, either in terms of doping of the different sites or the distortion of the structure, or layering as well. And we can play around also with different layering. We are now working and looking at also with Rados and Popper's system, and we saw that the difference. Obviously, if you change the intercalating layer between the perovskite slab, obviously you can change the system. And I hope I give you the feeling that oxidic compound can be used for this application. So with this, I finish my presentation. I would like to thank all my collaborators in ICSTEC and on Loughborough University that work on this system, and the Royal Society of Chemistry for the supporting, and you for your attention.
Thank you so much, Dr. Samson, and I think you have given us a very good overview of the possibility of perovskite oxide in the field of energy, and I thank you so much for this. Just let me ask if there is any question. We are just 2 minutes over our schedule. Any question? I know it's very difficult when we are online to make questions, so it's until now no questions. But okay, there is Giacomo. Thank you, Giacomo.
Hi, Plinio. Thank you.
Ciao, Giacomo. Ciao.
Plinio. Thank you for the very interesting seminar. I was listening to it very interested. Actually, I have a couple of maybe naive questions. I'm more involved in the halide perovskite, but still I studied some oxide and oxynitride. So first question is, do you think that working with oxynitride could help to improve the HER and OER reaction in your photocatalytic apparatus?
Yeah, probably, yes. Actually, it's something that we will work on it. We will start looking at it. For sure, the point is that you have to push the efficiency, keeping the stability. That is my opinion.
I understand. I deeply understand your point. So oxynitrides are terrible in that sense.
So yeah, but can obviously help the efficiency for sure.
Okay, and another question I have, it's related to the fact that you are using a very interesting compound based on copper. So still related to halide, sorry for this, you know, quite somehow logical parallelism, but actually, do you think that there are any possibility to observe any self-trapped excitons in such materials, those characterized with copper? I tell you because for halides, it's quite likely that self-trapped exciton phenomena can occur with copper dimerization. So I wonder if you...
Yeah, I mean, I didn't think of it, and thank you very much for the thing. Maybe we can have a chat together and look if there is it's a phenomenon that I didn't consider actually, but you're right. It can be something that can be there and can affect, especially with this change. I have to say that we are not, I mean, we are making some XPS measurements because we are not even very sure on which side you are going to when you are looking at the side. So
I would be extremely interested in taking a look if you have
yeah, sure.
And also, I would like to probably give an idea. I understand that these materials are very refractive from what you told before, but I wonder if there is any Stokes shift effect, because still double perovskite can...
Could be.
Yeah, so just in case, if you notice, let me know.
No, yeah, I appoint your name if you don't mind, and then we'll send you an email afterwards, because it's a very nice suggestion, and I would like to discuss you further.
Thank you very much. Very interesting. Congratulations.
Thank you.
Thank you, Giacomo, and thank you, Dr. Sanson. Thank you so much also for this exchange of opinions, scientific opinions. And let me introduce the last speaker of this morning session, which is Professor Lamberti from Politecnico di Torino. His presentation is about advanced nanomaterials for energy harvesting and storage, the happy marriage of dye-sensitized solar cells and the supercapacitors. Please, Professor Lamberti, we are here to listen to you.
This meeting is being recorded.
Good morning to everyone. I am Andrea Lamberti from Politecnico of Turin, the Department of Applied Science.
This meeting is being recorded.
Good morning to everyone. I am Andrea Lamberti from Politecnico of Turin, the Department of Applied Science and Technology. I'm working in the group of Material and Processes for Micro Nanotechnology in collaboration with the Italian Institute of Technology in Turin, the Center for Sustainable Future Technology. And today I will talk about advanced nanomaterials for energy harvesting and storage. I will describe you the happy marriage of dye-sensitized solar cell and supercapacitor for portable device. I switch down the camera. And in my research, and in our group, a big part of the activities related to some of the SDG, the United Nations select 70 Sustainable Development Goals that we as society must set to guarantee our future. And my research fall in 4 of them, 7, 11, 12, and 13. And I'm working in particular in the field of energy harvesting and storage. We are developing supercapacitor and integrated energy device with photovoltaics. Another part of my activity is related to blue energy harvesting and raw material recovery. And for both of them, I will focus attention on smart materials and a green approach, a sustainable approach, and sustainable technologies to carry on all these activities. In particular, today I will told you about energy device for harvesting and storage and the material that we develop for this kind of device, so metal oxide nanostructure and graphene-based material for the fabrication of flexible, wearable, and integrated energy harvesting and storage device. Starting from the harvesting section, the first device that I'm working on is the dye-sensitized solar cell. It is a photoelectrochemical solar cell developed in the last 25 years, and it is also known as the Grätzel cell. As you can see in this image, the cell is mainly composed by a photoanode, a wide bandgap semiconductor sensitized with dye molecules, an electrolyte, yodide redox couple, and a counter electrode. In both the cases, they can be transparent electrode with flowing dopantine oxide or other transparent conductive oxide on glass or polymer support. And when the radiation impinges on the photoanode, there is the charge generation and the regeneration of the dye thanks to the redox couple. In this kind of cell, the very important parameter is the recombination that must be overcome, and this can be obtained thanks to the creation of some particular structure like one-dimensional nanostructure, because in the traditional photoanode, you have a random network of titanium oxide or other wide gap semiconductor particles, and reducing the size of this kind of structure down to the one-dimensional structure, it is possible to improve the charge transport, reducing their combination, and improve the dynamics of the electrodes. These kind of cells are very versatile, as you can see in this image. They can be used for indoor device, or they can be easily integrated in building, like in this case. This is the convention center in the EPFL. And in order to improve the performance of this kind of photoanode, one possible solution is the exploitation of nanotubes, but in this case the nanotubes must be of wide gap semiconductor like titanium oxide, and we are working in particular on the anodic oxidation of titanium. These materials were firstly developed in 2001 by Professor Grimes. At the beginning, they are very short and rough nanotubes, but in the last decades, the performance is improved a lot in terms of production of this material. As you can see in this image, there was an evolution on the length of the nanotubes, on the order, and on the wall of the nanotube that can be more smooth and controlled during the synthesis. The anodic oxidation can be followed by looking to the current density versus anodization time. At the beginning, when the potential is applied, there is the formation of a compact oxide on top of the titanium surface, then the current reaches a minimum, some cracks and slits appear on the surface of the oxide, the electrolyte can reach again the metal surface, the current increase, and then stabilize. And in this plateau, there is the formation of ordered, vertically aligned nanotubes. The S-GROW nanotubes are completely amorphous, but the very interesting point is that you can select the crystallographic orientation of this material by simply changing the temperature of the post-treatment zone. By a thermal treatment at 450, for example, you can obtain a completely anaphase phase, and if you increase the temperature, you can reach rutile phase. This is a transmission electron microscope of the nanotubes, in which you can see the inner pore and a double wall structure, one more pores and one more compact on the external side, and after the thermal treatment, the formation of the crystallites in the wall of the nanotubes. We exploit these nanotubes for Dyson solar cell. In particular, we develop a strategy to grow the nanotubes on titanium foil in order to obtain thick membrane that was not possible to achieve on titanium thin film, and then remove the membrane from the titanium foil and move it on transparent conductive substrate like this FTO glass substrate in order to fabricate a semi-transparent photoanode for Dyson solar cell. It is possible to improve the charge transport by increasing the length of the nanotubes. Also, the efficiency of the cell is increased because it's increased the amount of material and the current density of this kind of photoanode. But more importantly, you can see the improvement of the electron lifetime with respect to titanium nanoparticles, and also the diffusion length, that is a very important parameter for this kind of cell. Another kind of structure that we developed is the so-called sponge-like zinc oxide. Zinc oxide is another good candidate for DSC. In this case, we deposit it in a porous configuration by RF magnetron sputtering, and it is a zinc layer, this black one, with coral-like or sponge-like morphology that can be then simply oxidized with a thermal treatment at relatively low temperature in air, preserving the morphology and allowing to reach also in this case an improvement in terms of electron lifetime and diffusion coefficient with respect to titanium oxide nanoparticles. And look into the architecture of the cell. We work a lot also in the fabrication of a flexible device. And in this case, you can see an example of flexible photoanode fabricated with a titanium foil with the nanotubes drawn on top. In this case, obviously, it is necessary a backside illumination of the cell. The down perimeter was transparent in this case, but the photoanode was a metallic foil. Or in order to achieve a semi-transparent cell, flexible, you can grow the nanotubes directly on titanium mesh. In this case, is a titanium grade. This is the top view, scanning electron microscope, and here you can see the cross section. This inner part is the titanium current collector, and here you can see the nanotubes vertically grown on top of the surface of titanium. What about the energy storage? We are working in the field of supercapacitor, that are energy storage device, alternative or in some case complementary to rechargeable batteries. In this Argonne plot, you can see the performance of this electrochemical capacitor that show specific power lower than traditional capacitor, but higher than rechargeable battery, and energy density lower than traditional batteries, but with a very large area of power and energy density that can be tuned by varying the material used for the fabrication of the device. The main applications are related to the automotive sector, to the energy storage from renewable energies and grids. The application to remote sensor that needs also a self-rechargeable working principle, and in particular also for wearable electronics. In our research group, we focus attention on the selection of advanced material with a sustainable approach for the fabrication of sustainable energy storage device. In particular, energy storage devices like batteries, but also supercapacitor, usually employ toxic solvent like NMP for the fabrication of the slurry that must be removed and recovered, and it impacts on the cost of the device. We propose an alternative following a water processable supercapacitor and exploiting active material derived by biomaterial and bioderived polymer as binder in order to achieve a completely green process, lowering the cost of the device and reducing the environmental impact. We are working on the electrodes, on the active materials, so bidimensional material, metal oxide. We work on several kinds of electrolytes, from water-based up to polymeric-based electrolytes, and also on the packaging with customized architecture, flexible, also wire-shaped, and we characterize the device by an electrochemical and electrical point of view. All these processes well conducted with a water-based process and green material. Some example of the material that we have developed in the past years are is graphene aerogel, since the electrodes of supercapacitor needs to exhibit high electrical conductivity, controlled porosity, and high surface area, exposed area. Using graphene and obtaining an arrangement in a three-dimensional architecture, it is possible to improve the performance of the device. This process is very simple. We start from a graphene oxide dispersion in water, and by hydrothermal reduction, we can achieve an hydrogel that can be then transformed in the aerogel through a freeze-drying process. By adding inside the solution some precursor of metal oxide or metallic alkogenides, it is possible also to obtain a carbon-based aerogel decorated with pseudo-capacitive material. And this is the case of molybdenum disulfide that we have investigated in the past. In order to lower the cost and reduce also the environmental impact, also in this case, we move on the process and we change the traditional hydrothermal treatment with a microwave treatment. Another example of sustainable electrode for supercapacitor, in this case for micro supercapacitor, is the so-called laser-induced graphene that can be obtained by direct laser writing of some polymers. Aromatic polymer are the best choice for this process, and it exploits a photothermal effect. CO2 laser in the infrared wavelength range is used, is a pulse laser, and thanks to the absorption of the photons by the material, it is possible to convert the surface of the material in a graphene-based material. It's a few-layer graphene sponge with a high surface area, good conductivity. Also in this case, it is possible to decorate the material with pseudo-capacitive material and fabricate a device that can be also directly connected in series or parallel by exploiting the same material for the connection. So it is a binder-free material with a very fast processes. It is a one-step direct laser writing. It is also possible to fabricate not only flexible but stretchable devices. In this case, is an example of laser-induced graphene on PDMS, obtained by direct transfer, peeling off the leak from the Kapton substrate, and in the fabrication of the flexible device that can be also stretched up to 50%. But it is also a good candidate for high temperature application. It is a very interesting sector for supercapacitor. In this case, is an example of micro supercapacitor, totally flexible and able to sustain up to 100 degrees Celsius. Considering these two devices, the Dyson synthetic solar cell and the supercapacitor, we start working on integration of these two devices in order to answer to the request of a particular sector. And this is the case of the large wireless sensor network of the Internet of Things, in which there are a lot of connected sensors that must be powered by disposable or rechargeable batteries, but the maintenance in some cases can be difficult or expensive, and so we are trying to fabricate a portable power pack that can be directly recharged by the environmental energy source, like indoor or outdoor light. In particular, the idea is not only to connect a single device, but to integrate the two devices in order to exploit both artificial and natural light in a single device. We select these two technologies because Dyson synthetic solar cell show very high conversion efficiency in indoor applications, so reducing the impinging light, the efficiency increase, and they can be easily integrated with other electrochemical energy device. And so since both supercapacitor and Dyson synthetic solar cell are electrochemical or photoelectrochemical device, they can sustain a similar fabrication process, and they are more sustainable and safer with respect to batteries, for example. With our technology, we want to reduce the energy need by a self-powering of the device with solar energy, indoor light, and possibility of a remote placement of our devices. We work with in the beginning single cell stack with the same fabrication process. Then we move to innovative design and fabrication of modules, and then the fabrication of flexible device in transparent packaging. And here you can see some details about the first device that I showed you before, in which we exploit almost the same material, so PDMS packaging, metallic grid, titanium grid for the DSC, and stainless steel grid for electric double layer capacitor, and both are closed in the same elastomeric substrate in order to obtain this flexible device in which it is possible to see the photo charge of the device and the discharge to power sensors. And good performance is also in terms of bendability of the final device. Concerning the second device in which we show the fabrication of a module, we exploit the same substrate. This is a rigid architecture on FTO glass substrate, and the device are sharing the electrodes since they are directly deposited on the same substrate. And as you can see here, there are 5 cells connected in series. The efficiency of the final module is not so high in traditional one sun illumination condition, but if you reduce the light down to 21 watt per square meter with a LED illumination, you can achieve a 13% of efficiency of the module with a good OPEX. It is the overall photoelectron conversion and storage efficiency. So combined efficiency of photo generation and energy storage with a stable behavior in time up to, in this case, we stop the measurement 6,000 cycle, and good performances in particular in indoor condition. In conclusion, we are working on nanomaterials and configuration and architecture of this kind of device, in particular, looking to the sustainability and the scalability of this technology, trying to improve the charge transport properties of the material, and look into the architecture, fabricating flexible devices, in some cases also stretchable, with good stability and low cost, in particular with low environmental impact. The integration, in our case, is focused to the Internet of Things sector to power portable sensor for remote application. I would like to acknowledge all our partners and thank you very much for your kind attention.
Thank you so much, Professor Lamberti. Very interesting. I think you have touched two very important and amazing questions, which is the low cost and low impact, so green synthesis of the material. So it was, I think, particularly interesting. We are at the end of this morning session before a coffee break. It's a virtual coffee break, unfortunately. We cannot have a coffee together. But let me ask if anybody has any question for Professor Lamberti now. Okay, let me thank again Professor Lamberti for this nice, very interesting presentation. And I invite you for the coffee. Sorry not to be in presence to drink together, but it's a virtual coffee. I think still we can enjoy. And see you later at the second session of the conference this morning. Thank you. Bye, everybody.
Okay, thank you. Enjoy. Bye.
Okay, so welcome back from the coffee break. I hope you are all here. I'm Alessandra Sansone and I will chair this section before lunch. We will suddenly start with Stefano Agnoli of Padova University with a presentation titled Exploring the Flat Land of 2D Materials by Electrochemical STM, Visualization of the Active Sites for the Hydrogen Evolution Reaction with Atomic Scale Precision. Please, Stefano, the floor is yours.
Good morning, everybody. First of all, I want to thank the organizer for the opportunity to present here some new results by our group about a new technique based on scanning probe microscopy that can be used to investigate with atomic scale precision in operando condition electrocatalytically active materials. As case study, I will show you some results about the identification of active sites for the hydrogen evolution reaction on different two-dimensional materials such as graphene and transition metal dichalcogenide. So the instrument that allows to combine inoperando investigation in an electrochemical environment and atomic resolution is the electrochemical STM that you can see in this picture. As you may see, it is a very simple and somehow rather an extraordinary tabletop instrument, but in the following I will try to convince you that this simple instrument has a very huge and still untapped potential in electrocatalysis. Just for comparison, consider that high-resolution transmission electron microscopy has the same potential for spatial resolution down to the atomic level. However, TEM cannot be used in operando condition in an electrochemical environment. On the other hand, other techniques that can be used in an electrochemical environment, such as FTIR or X-ray absorption spectroscopy, cannot have atomic resolution down to the atomic level. So here we can see the operating principle of electrochemical STM is essentially an STM where the tip has been coated by glue in order to prevent the interaction with the electrolyte. Essentially, it is a 3-electrode electrochemical cell where the working electrode is the surface probed by the tip. So you can investigate a material in presence of the electrolyte at different electrochemical potential. However, how can a microscopic technique provide information about catalytic phenomena? So the idea goes back to the very beginning of STM and to the work of the Nobel Prize winner Gerd Binning, who, while studying the reactivity of metal surfaces in ultra-high vacuum conditions, for the first time had the intuition that the noise that is consistently observed during imaging is not really an undesired artifact or the random noise, but actually it can be connected to some dynamical process taking place on the surface, such as the diffusion of oxygen atoms or oxygen reactivity. And this idea was further elaborated in the context of electrochemical STM by Professor van der Renke from the University of Munich. And in a very nice Nature paper, he demonstrated that the noise in the tunneling current during STM images could be connected to the electrocatalytic current. To demonstrate this, he acquired STM images of the platinum-11 surface at different electrochemical potential. So at more oxidizing potentials where the HER doesn't take place, the resolution of the surface is normal. You can see flat line profile. But when the electrochemical potential is set in the range where the HER can take place, van der Renke could observe a distinct noise in the images that was localized on the most active catalytic sites that are the step edges. You can see here clearly, very clearly the presence of spikes and noise. So we took the cue from here and decided to investigate the activity of some two-dimensional materials by electrochemical STM. Among two-dimensional materials, transition metadichalcogenides such as molybdenum disulfide or molybdenum diselenide are known to be very active catalysts and the most likely substitutes for platinum in the hydrogen evolution reaction. In the past, together with Matthias Batz's group at the University of South Florida, we have investigated this material and reported the presence of some special type of line defects called metallic twin boundaries, MTB, that are easily formed on these systems, and they have very special electronic and structural properties, and therefore a very high chemical activity, especially in the hydrogen evolution reaction. So on this image, you can see an STM, electrochemical STM image of atomically resolved molybdenum diselenide thin films grown on graphene taken in 0.1 molar perchloric acid. So the bright triangular features are the metallic twin boundaries, but given the atomic resolution, we were also able to observe point defects such as selenium vacancies, as you can see in this image. So we decided to see what happens when we change the electrochemical potential from the double layer region towards more reducing condition where the HER can take place. So in this movie, you can see on the left the evolution of the STM images as a function of the electrochemical potential, whose position is given by this blue dot that is moving along the microscopic CV. So you can see that when the electrochemical potential approaches catalytic condition, we see more and more noise and even very fuzzy areas, and eventually some sort of effervescence of the surface, but not everywhere, just on selected areas where there are the MTBs or the defects. And this behavior is quite reversible with electrochemical potential, so the noise disappears in the double layer region. You can see here we have a lot of noise, and here then we go back to the double layer region, the noise strongly disappears. So anyway, fuzziness, noise, effervescence are not really quantifiable physical quantities. Therefore, in order to analyze the SC-STM images, we define a new quantity, L0, that we call current or topographic roughness, which is simply the absolute square deviation with respect to a reference value, which can be measured on each X and Y pixel of a certain area of interest that in general encloses some interesting area of our surface. In the case of the current images, we took as a reference value the current that is set in the STM feedback loop, and we obtained for L0 this kind of expression. And to make this quantity independent from the size of the sample area, we normalize it to the area A of the defect and to a factor K that takes into account local corrugation effect. And finally, we took as 0 the value of the roughness at the electrochemical potential when the reactions are off. That is the value L0 off. So this type of quantity can be calculated on any area of interest and at any potential, obtaining some L versus electrochemical potential curves. And since the catalytic current is a first-order perturbation of the tunneling current, these curves provide us with a local map of the electrochemical activity, as I will show you in the following. So we went back to the previous experimental data and we calculated the plots of the current roughness versus the electrochemical potential, as you may see here, on each of the defects and interesting part of our surface. You can see here the vacancy, the MTB, and 2 types of defects, vertex 1 and vertex 2, that are 2 different crossing of the MTB. And through this type of course, we can identify the potential necessary to trigger the HER and therefore the onset for the HER activity of these different defects. So the most active defects is vertex 1, followed by vertex 2 and the vacancy, and finally by the MTB. So we compare the activity deduced by these plots with the absorption energy of a hydrogen on this structure that was calculated by Arkady Krashenikov from Aalto University by means of DFT calculation. Actually, it is well known in the literature that the highest activity for an HER catalyst is observed for the most thermoneutral absorption energy. And according to calculation, its minimum is observed in the case of a vertex 1, as you can see here, which is followed by the vacancy and vertex 2 with almost the same hydrogen absorption energy, and finally by MTB. So we have the same order of reactivity and even the same reactivity predicted for the vacancy and vertex 2, exactly like in the experimental plots. So we decided to test, we were very excited and we decided to test our method on a different material, and we decided to apply this method to identify and compare the activity of active sites in a graphene-based system, and in particular on iron layer deposited on the platinum-11 surface covered by a graphene layer. You can see here a schematics of the system, graphene, iron, and the platinum surface. And here are reported some UHV STM images of such a system. Interestingly, as you can see from these LSVs, on the left, when the platinum surface is covered by graphene, its activity in the HER strongly decreases. You can see the red curve. On the other hand, when iron is covered by graphene, its activity is boosted, and the system is almost as active as the clean platinum-11 surface, which is an excellent catalyst for the HER. So the results are in agreement with a very rich literature reporting that the interfacial hybridization effects between the metal layer and graphene can really boost the activity in the HER. Here, I'm reporting some electrochemical STM images of the graphene layer covering iron films supported on the platinum-11 surface. Here in this area, you can see graphene simply on platinum. Here you can see a step edge. Here we can see an iron island covered by graphene, and we were also able to resolve some point effects that are made up by single atoms of iron trapped into vacancies within the carbon layer. So the identification of these defects has been obtained by comparing the simulation made by DFT of the STM images. So here we can see again a movie obtained following the previous area as a function of the electrochemical potential. On the right, again, you can see a macroscopic LSV with a red dot showing the potential. And here on the bottom, you can see a 3D rendering of an area that is centered on this atom of iron trapped into a vacancy of carbon. So here you can see as a function of the electrochemical potential, the evolution of the surface. You can see the increase of noises and spikes in the image as the potential is decreased. So from this kind of movie, we were able to extract the current reference plots reported here in the bottom right panel. And from these plots, we can deduce that the most active sites are the single atom of iron trapped into the vacancies, followed by the step edge covered by graphene, and then iron covered by graphene, and only finally platinum covered by graphene. Once again, we call on theory to validate the experimental results. In this case, Cristiana Di Valentin from the University of Milano Bicocca modeled a different structure and calculated the hydrogen absorption energy whose value are exported here in this table. And once again, the agreement with the local current roughness measurement is simply perfect. As you can see, the lowest absorption energy is observed for the single atom of iron trapped into the vacancy. Then we have the step edge. Then we have the iron layer covered by graphene. And finally, graphene covering the platinum. So I hope that I convinced you that electrochemical STM is an extremely powerful technique that allows to investigate in operando condition electrocatalytic processes with atomic scale resolution. Also, by using our new quantity, the current roughness, we can directly evaluate the catalytic activity of different structures on the surface. And this is very important because it allows to really change the perspective of electrocatalysis from area average data to activity measurements even on single atom sites. Finally, I want to thank the person who made possible this study, in particular Tomasz Kozmale and Marco Lunardone acquired the STM images, the theoretician from Alta University Milano Bicocca, and Matthias Batzil from the University of South Florida for the transition metallic cogenite sample. And I want to thank you for your attention.
Thank you very much, Stefano, for this very interesting overview of this very powerful technique. Is there any question from the audience for Stefano? Actually, I have a curiosity, if I may. What is the maximum area that you can analyze with your technique?
So the maximum area we can reach up to micrometer. We are limited by the scanner of the STM. It really works like a standard STM. So from the micro, of course, the resolution is not as good, and down to the atomic level. In general, we use tens of nanometer by tens of nanometer because we really want to focus on something very, very, very small.
Well, very nice. Thank you very much. If there is no questions, I don't see any questions, so I thank Stefano again, and we can move to the other speaker of the morning, that is Gianmarco Enrico Griffini from the Milan Polytechnic with the presentation called Advanced Polymeric Coatings in Photovoltaics, Assessing Multifunctionality for Improved Device Performance.
Good morning, everyone. So let me start by thanking, first of all, the organizers for inviting me to present our recent activities on polymeric coatings for photovoltaics. I'd like to start my talk of today by sharing with you a brief overview of the role of polymers in the energy conversion field. As we all know, polymeric materials have been employed extensively in photovoltaics for many purposes, some of which have been reported in this slide. So if we look at the last generation of solution processable solar cells, mainly organic-based solar cells or hybrid solar cells, I think we can all agree on the fact that they all present several advantages compared with inorganic counterparts. However, most of them are relatively poorly stable, in addition to having, in some cases, limited spectral breadth in terms of photoactive material. So one approach to tackle such limitations may be to develop tailored multifunctional coating materials based on suitably designed polymers. In this respect, a particularly interesting class of polymers are the so-called UV curable or photo-cross-linkable polymers, which are already present in several application fields and are characterized by the high curing speed and the possibility to implement such systems on an industrially relevant scale in a relatively straightforward fashion. So building upon these characteristics, one way to exploit the versatility offered by polymeric materials and extend the application potential of photo-cross-linkable systems is to develop UV curable polymeric coatings which can incorporate optical functionalities through the so-called luminescent downshifting, in which a luminescent species embedded in the coating material absorbs high-energy UV photons and re-emits these absorbed photons redshifted, typically in a region where the photovoltaic material may exhibit optical spectral response. So in my talk of today, I will try to focus on application of these types of coatings, photo-cross-linkable, incorporating luminescent downshifting capabilities, in 4 different photovoltaic fields, as shown in the slide. And I will start with a description of our work on a particular type of UV curable coating used for dye-sensitized solar cells. Such coating system is based on a fluoropolymer precursor that is appropriately functionalized by addition of a methacrylate functionality that allows for UV-mediated cross-linking. So basically, we are introducing a double bond as a pendant group in this fluoro-trifluoro-vinyl ether polymer backbone. To include the luminescent downshifting functionality we have just talked about, a europium-based complex was synthesized because of the large Stokes shift, the high luminescent quantum yield, and the wide spectral breadth that exhibits in the UV region. In order to exploit the optical characteristics of this EU complex for luminescent downshifting purposes, an indolin-based organic dye was selected because it was shown to give promising performance in flexible dye-sensitized solar cell devices, and because it shows excellent match with the spectral characteristics of the europium complex, as you can see here. So the concentration of this europium complex in the coating, in the CTFE vinyl ether polymer-based coating, was systematically varied, and its effect on device performance was evaluated. As you can see from the plots in the slide, An increase in short-circuit current density is observed at increasing europium content, which is found to be maximum for concentration in the range between 1 and 2 weight%. Similarly, a corresponding increase in device efficiency is observed, resulting in a remarkable 70% increase compared with uncoated control devices. In parallel, a clear stabilizing effect of the applied coating on such solar cells devices can also be observed, as you can see here. So where basically we are plotting the evolution of device efficiency over real outdoor exposure conditions. You can quite clearly see that the coated devices maintain their initial performance even after more than 2,000 hours of outdoor exposure, as opposed to what happens to control devices. This behavior demonstrates the excellent stabilizing effect of our fluorinated coating system. Moving on to a more recent type of devices, so-called perovskite solar cells. Also in this case, we developed a coating system with a similar structure as the one discussed earlier. However, in this case, a perfluoropolyether-based dimethacrylate, as you can see down here in the bottom of the slide, was also incorporated in the coating formulation, so as to further reduce the surface energy of the coating itself, thus making it highly hydrophobic, thus potentially applicable as protective coating for perovskite solar cells, which are notoriously unstable when in contact with water. So by carefully controlling the relative proportions of the coating components, a monophasic transparent material could be obtained. And transparency in this case is highly required, considering that these coatings will serve an optical function. Once again, the idea was also here to propose a polymeric coating capable of providing an optical functionality to the system. To do that, luminescent downshifting was also targeted. In order to add such spectral conversion functionality, the coating formulation was completed by adding a commercially available luminescent organic dye, as you can see here in the slide, belonging to the Lumogen family, which absorbs in the UV spectral range and emits by-fluorescence in the visible range. This should ensure optimal match with the spectral response of the perovskite solar cell. Such coating was then deposited on the glass side of the solar cell device, and the efficiency and stability of the coated solar cells were assessed. As you can see from the plots, by tuning the amount of fluorescent molecule in the coating, a 5% increase in efficiency compared with the uncoated devices could be achieved. Particular 2% maximum incorporation of organic dye was found to deliver the maximum efficiency. And this is mainly resulting from the enhanced spectral response in the UV region of the solar cell, as you can see from the EQE spectra. Also, by subjecting such coated devices to different aging conditions, the excellent stabilizing effect of this coating material could be clearly demonstrated. Indeed, coated devices exhibited excellent retention of the initial performance, both under accelerated UV weathering and when exposed to outdoor aging. Clearly, the coating enables enhanced UV screening effects because of the presence of the fluorescent molecule, and also moisture barrier effect can be provided thanks to its low surface energy, which derives from its chemical composition, that also allows easy cleanability of the device, thus enhancing the outdoor performance on a long-term basis. So to further prove the versatility of this type of approach, luminescent solar concentrators were now considered. This technology can be looked at as a sort of auxiliary technology to photovoltaics, in which a polymeric slab or a coating incorporates a luminescent material which is able to absorb incident sunlight and re-emit it by fluorescence. The slab or coating then promotes the wave guiding of such re-emitted light towards the edges, where photovoltaic cells are typically placed for the photon to electron conversion. In this specific case, the fluoropolymer coating formulation was further modified in order to enhance its surface properties by lowering further its surface energy by the addition of a perfluoroacrylate moiety, as you can see here. A dedicated functional fluorophore was then developed, you see it here in the slide, mimicking the most commonly employed material for LSCs in terms of fluorophores, which is Lumogen red, here depicted in red, but exhibiting carbon-carbon double bond functionalities, allowing for covalent incorporation in the polymer matrix during UV curing, so participating in the cross-linking process. The surface properties of the resulting fluorescent coating were found to promote self-cleaning, given the extremely low surface energy of the highly fluorinated UV curable matrix. This is clearly of interest in view of a potential application of these systems as light conversion paints or varnishes or coatings for outdoor structures and for architectural elements. In addition, the possibility to incorporate the luminophore through covalent bonds during coating formation allowed to increase the photostability of the overall system, even after more than 800 hours of continuous sunlight exposure. This response was evident, especially when comparing our new co-cross-link system with controlled system, in which the luminescent solar concentrators is based on the same UV curable matrix, but it incorporates Lumogen red in a host-guest fashion, so not co-cross-linked with the matrix. This indicates that the limitation of the molecular motion within the highly cross-linked structure promotes photostability of the co-cross-link systems, thus enhancing its prospective use outdoor. Finally, to move on to organic photovoltaics, a slightly different strategy was proposed in this case, relying on photocurable coatings based on the sol gel chemistry. So in this case, the coating material was based on a fluoropolymer precursor, the same chlorotrifluorovinyl ether resin that we already explored so far, but in this case, adding a methacrylate functionality to the coating, to the formulation, so as to allow for UV-mediated cross-linking, but also incorporating a silanol moiety that allows for the introduction of a sol gel precursor. So basically, the idea here is to exploit the interaction between the UV light during the photocuring process to open the double bond in the methacrylate moiety. The exothermicity of this double bond opening should provide and provides locally the heat necessary for the condensation reaction of the silanol group, leading to a three-dimensional hybrid organic-inorganic network, as shown schematically in this part of the slide. So we have an organic-inorganic three-dimensional network that we expect to provide higher photostability to the system without resorting to thermal annealing, which is typical of sol gel processes. To include the luminescent on-shifting functionality, an organic dye was synthesized, as you can see here, and incorporated in the hybrid coating material. Such species is shown to give excellent matching with the optical properties of the photoactive layer of the organic solar cell that we have used, which is based on the conventional bulk heterojunction between polythiophene and PCBM. So the concentration of the luminophore in the coating was systematically varied, and its effect on device performance was evaluated. Here you can see the external quantum efficiency, how it varies by increasing the amount of luminophore in the coating. As you can see, we observe an increase in the external quantum efficiency at increasing dye content, found to be maximum for a concentration of 1%. This resulted in a correspondingly higher short-circuit current density and device efficiency, which led to a 4% increase in performance compared with uncoated control devices. Similarly to what observed on the other photovoltaic technologies discussed earlier, also in this case, the incorporation of such fluorinated coating material was found to lead to a significant increase in device stability. In fact, you see here the black trend, which is our luminescent dose shifting OPV system, as opposed to encapsulated conventional systems and non-coated devices. So these trends further confirm the excellent stabilizing effects also of this sol gel-based luminescent dose shifting coating system, thus demonstrating the validity of the approach we have discussed so far. So based on the overview of our recent investigation in the field of multifunctional coatings for solar cells, I hope I have convinced you on the role of polymers in solution processable photovoltaics, especially as versatile platforms for improved reliability and added multifunctionality for our photovoltaic systems. With this, I'd like to conclude, and I would like to thank all the people who contributed in this project, my past and present collaborators, the funding agency, and of course you all for your kind attention. Thank you.
Thank you very much for this nice overview of the different polymeric coatings that we can apply for the energy system. Is there any question for the Marco from the audience? So I have one. In which way are you commonly depositing your polymers for different applications? You said also something about paint, no? That would be very nice. Which are the most common way in which you can apply your coatings?
So in the cases I have shown, lab scale devices are deposited by spin coating. That's the easiest way to do it. But we have also done spray coating, we have done bar coating, wire coating, deep coating. So basically, potentially any type of coating technique.
So you don't have any influence on the process, on the deposition, you think?
Well, yes, I mean, depending on the level of, the amount of solvent you're using, this will definitely affect the underlying layers. So it depends on, on the level of dry to solvent concentration, then one should choose one technique with respect to the other. Spin coating is good in this sense because you can control you can reduce significantly the amount of time where the solvent is in contact with the underlying layer. So if you're depositing on top of something that is typically soluble, then this is an issue. But of course, you can change the formulation of the coating to make it fully dry, let's say, with no solvent in it. So that's another option.
It's really versatile then.
Yeah.
Okay. Thank you very much. If there is no other question from the audience, no, so we can move on to the next speaker, that is Alessandro Facchin from Padua University. His presentation is titled Oxygen Reduction Reaction Monitoring at Iron Single Site Catalyst, Electrochemical Scanning Tunneling Microscopy of Iron Octa-Ethyl Porphyrin.
Yes, thank you for the opportunity. So my name is Alessandro Facchin. Today I'm presenting my research topic concerning the oxygen reduction reaction monitoring at an iron single site catalyst. It is basically a CSTM, so electrochemical scanning tunneling microscopy study of an iron octa-ethyl porphyrin. And in this presentation, we are going through the analysis of an HPG functionalized iron octa-ethyl porphyrin functionalized HPG surface, which will act as a working electrode, and it will be probed versus the oxygen reduction reaction and CSTM will be presented as an inoperando technique, but electrochemical techniques like cyclic voltammetry and rotating ring and disc electrode will be also presented as complementary techniques which provide and complete the information coming from the electrochemical point of view. And in fact, from the voltammetric investigation, we will extract information about this iron 2, iron 3 redox process, which is at the basis of the oxygen reduction reaction on these systems. And finally, there will be some remarks on computational data coming from BFT and molecular dynamics to theoretically describe oxygen reduction reaction on these systems. So why porphyrins? Porphyrins are good model systems, good molecular systems to describe a single site catalyst, a single atom catalyst, and in fact metals can be easily stabilized and coordinated by the nitrogen donors typical of porphyrins, and porphyrins, metal porphyrins can represent good model system for a metal nitrogen doped carbon powder. And here on the right there is an example in which we have a graphene sheet and we have some nitrogen doping which coordinate an iron, and they form an iron nitrogen 4 sites site. And these materials, metal nitrogen doped carbons, are emerging as valid alternatives with respect to platinum group materials as catalyst materials for fuel cell and metal batteries, for example. And in fact, platinum is still the most performing material in terms of performances, but its presence should be avoided basically due to its high cost and to its low availability. But regarding metal nitrogen carbon systems, there is still a knowledge gap. There is still a lack of information regarding the real active sites and regarding the selectivity of these sites, especially two main reaction mechanisms can be individuated, the 2-electron mechanism and the 4-electron mechanism. For a fuel cell, the 4-electron mechanism should be preferred because it leads to the production of water as a reaction product, whereas the 2-electron mechanism will lead to the production of hydrogen peroxide, which for our final application should be avoided due to its oxidizing properties towards the membrane electrode assembly of a fuel cell. So how we built a model system to be studied for this oxygen reduction reaction in a CSTM. First of all, we need a suitable molecule. So the porphyrin itself can be coordinated with iron, and it gives us this iron nitrogen 4 site. But we also need some external, some peripheral substituents. In this case, they are alkyl groups, ethyl groups, because they help the physisorption process on the substrate, on the HOPG. They act as anchoring groups. And the HOPG itself is a suitable substrate for a scanning probe microscopy technique because it's very flat, it's not so sensitive to airborne contamination, nor it's sensitive to specific anion absorption. And from the electrochemical point of view, it's not active towards the oxygen reduction reaction, or at least it's not active in the potential window desired for the metal porphyrin. And a CSTM, as I was mentioning, is acting as an inoperando technique because we have our tunneling tip, which is put in close proximity to our solid substrate, which is HOPG. This substrate is functionalized, so we have our monolayer of porphyrins, iron octatyl porphyrins in this case, and we have the solid liquid interface. In particular, we have an electrolyte, so 0.1 molar HClO4, and therefore this iron octatyl porphyrin functionalized HPG surface acts in the same time as probed surface by STM, but also as a working electrode surface because it's in an electrolytic solution, and we have also a counter electrode and a reference electrode. So we definitely have 3 electrode setup plus the addition of the tunneling tip, which is a fourth, actually the 4th electrode, and that's why it should be coated with glue to isolate it and prevent additional Faraday currents. I start giving some information on the electrochemistry part. From the cyclic voltammetry, we can clearly understand that there is a reversibility effect of the iron core. In fact, we are at the reversible hydrogen electrode scale, which is also the standard hydrogen electrode electrode potential, since the pH is equal to 1. At 0.4 volts, we have this redox couple. Actually, the oxidation peak it's not so intense, probably due to a slow reoxidation. But in the end, there is a quasi-reversible behavior of this iron center at this potential. And in fact, if we look at the corresponding cyclic voltammetry obtained in oxygen-saturated electrolyte, we have this blue voltammogram, so the iron octatyl porphyrin layer in oxygen-saturated electrolyte. We have this huge catalytic peak at potential a little bit more negative than the corresponding argon case, indicating that this redox couple, that the redox effect triggers in some way the catalytic activity. It must be remarked that also the free base molecules, so without any metal atom in the inner cavity, possesses some kind of a weak activity towards the oxygen reduction reaction, mainly due to the nitrogen pyrolytic sites, or also to the orthocarbon near these nitrogen atoms. And of course, the HOPG is completely flat in this potential window. The additional characterization comes from RDE measurements, rotating ring and disk electrode. We have a glassy carbon disk, so still a carbonaceous materials, can be in the same way functionalized with the analyte molecule, so iron porphyrin. And we have a platinum ring which oxidizes any eventual hydrogen peroxide molecule formed at the disk electrode. And we have this linear strip voltammetry on the right, both for the iron and also for the free base, which turns into this hydrogen peroxide production. For iron, we have a very low hydrogen peroxide production, lower than 10%, whereas for the free base, we have around 30%. And in fact, it translates into a number of exchange electrons almost equal to 4 for the iron octatyl porphyrin, and almost equal to 3 for the free base porphyrin. But if we focus on the iron porphyrin, then we can understand that the main reaction pathway goes through the 4 electron mechanism, so it's suitable for a final fuel cell application, because the main reaction products is just water, no hydrogen peroxide is produced. Focusing now on the STM, here I reported some large-scale images just to point out the effect of the absence or presence of the iron. Here we have iron and we have some defects, and we have some different unit cell parameters compared to the free base case, where we have a more uniform layer. We have this kind of alternating rows, but it's just the twisting of the molecules with respect to the molecular line. And then we have an intermixed system here on the right, which will help us in the next slide to understand oxygen absorption. We start with the free base compound, the free base molecule. And here I reported the corresponding cyclic voltammetry in oxygen-saturated electrolyte. This means that the instrument can record STM pictures, and I reported here in the bottom part, but at the same time we associate them with a precise electrode potential that we can extract from a cyclic voltammetry, and that's why we have, for example, this image on the left at positive potential. We are here in the CV, nothing happens from the cyclic voltammetry, and in fact we have a stable layer. We clearly see molecules. They have a dark spot in the center because no iron is present inside them. But the same situation occurs also at negative potential. We are here in the CV 0.2, close to the cyclic to the oxygen reduction peak, but the layer is still stable, and still we have an hollow cavity in the center. And again, sweeping back the potential to 0.55, so positive potential, nothing happens. But this system is meant to be a reference for a further experiment. Now let us focus on the iron, on the pure iron octatyl porphyrin layer, and it is clear here that we have a very bright, intense spot, sharp spots in the center of each molecule, and in fact we can trace a topographic profile and extract a protrusion in the order of 100 picometers, indicating the presence of an iron core in the center of each molecule. The situation changes in a oxygen-saturated electrolyte. If we expose this layer to an oxygen-saturated electrolyte, then we have again molecules, but we have a larger spot. It is shifted from the molecular center, and the associated protrusion is lower, is almost half of the initial value. We are in the order of 40 to 60 picometers. And this is coherent with a mechanism like this one depicted in the center. So oxygen comes in contact, in proximity of the iron center, and eventually it forms a complex with a mostly like end-on geometry, with just one oxygen atom binded to the iron core. And then if we look at the intermixed system, so we have a mixed layer here on the left. We have a dim molecule associated to the free base porphyrin, which did not show any contrast difference in the CSTM. And then we have these brighter molecules, which already saw we can associate to the iron-oxygen complex because the protrusion, the topographic profiles are coherent. And then we reduce the potential to 0.35. We are here in the CV, close to the ORR peak, and the topographic profile, okay, the contrast is fuzzy, the image is not clear because we have a lot of current going on, but at least the topographic profile change, and in the end, we don't have any oxygen absorbed at this potential because there is a continuous turnover of the catalyst. And finally, sweeping back the potential to a positive, sufficiently positive value, we restore the initial situation with oxygen absorbed on the catalytic side. Finally, some remarks on computational data. First of all, chloride is computed to be lost during the deposition state, so we are basically dealing with an iron 2, with a pure iron 2 octatyl porphyrin layer, which then reaches some coordination with water and eventually with oxygen if we saturate the electrolyte, then some other elementary steps leading to this 2-1, the C and C first. The C leads to the formation of water, and C first leads to the formation of hydrogen peroxide. But if we look at the Gibbs free energy steps, we see that hydrogen peroxide formation is just weakly energetically favored, whereas a big energy gain comes from water production. So this is coherent with what we already saw by rotating ring and disk electrodes. So theory matches experiment in this case. So I concluded my presentation. I want to thank the Electrocatalysis and Applied Electrochemistry group, to which I belong, at the Department of Chemical Science, University of Padova. I'm here on the left, and the smallest person here is my supervisor. Thank you for the attention.
Thank you very much, Alessandro, for your nice presentation. Is there any question from the audience? If not, for the sake of time, I will move on. Thank you again, Alessandro, for your presentation. And we can move to the other presenter, that is Emilia Paone from the Mediterranean University of Reggio Calabria. The title of her presentation will be Spent Lithium Cobalt Batteries, Efficient Heterogeneous Catalyst for the Reductive Upgrade of Biomass-Derived Furan.
Good morning to everybody. First of all, I would like to thank the organizing committee for giving me the opportunity to present the results of this research, in which we reuse and recycle the black mass derived from the spent lithium cobalt batteries as an efficient heterogeneous catalyst in a circular economic view. In the last year, in fact, we have witnessed a lot of research effort from both academia and industry players in the recycling electronic waste. And since cathode material in lithium-ion battery contains transition metal elements such as cobalt, manganese, and nickel, in which these elements are usually used for catalytic reaction, so cobalt oxide species represent a valid resource for the preparation of cobalt-based catalysts. Cobalt, in fact, has been largely adopted for several catalytic reactions, including Fischer-Tropsch, electrochemical wood splitting, reforming, hydrogenation, and many others. By now, only few attempts are present in literature in the use of cobalt-based catalyst directly obtained from spent lithium-ion battery, mainly devoted to the promotion of oxidative reaction. And the aim of the proposed research is to demonstrate a possible reuse of spent lithium cobalt batteries as efficient heterogeneous catalyst for the reductive upgrading of different lignocellulosic biomass-derived molecules that has been not studied so far. Reductive catalytic processes gain a lot of attention since once the lignocellulose is deconstructed, cellulose, hemicellulose, and lignin fraction can be subsequently converted into platform chemicals that can be further transformed into target molecules, added chemicals, solvent, and materials. Lithium cobalt batteries was tested after a mechanothermal treatment. After a first ball milling process, the milled sample was filtered by using a sieve screen mesh and calcined under atmosphere condition at 550 Celsius degree for 6 hours. Before catalytic test, black mass was finally reduced at 500 Celsius degree for 6 hours under hydrogen flow. The black mass catalyst was fully characterized by physicochemical characterization, in which elemental analysis was determined by both ECP and XRF technique. And the main elements were found to be cobalt, nickel, and manganese. On the other hand, FESM EDS analysis show a well-graded grain size distribution and an irregular morphology. EDS analysis reveals the presence of distinct metallic species, with those related to cobalt that was characterized by round particles that remember the form of beans. XRD analysis confirmed the reduction of cobalt and nickel oxide, while at the same time the presence of manganese oxide can be noticed. And finally, TPR profile is characterized by a broad and intense peak related to the simultaneous reduction of cobalt and manganese cations, with the latter occurring at about 600 Celsius degree. The choice of the substrate investigated arises from that furans represent one of the most important classes of intermediate in the conversion of non-edible lignocellulosic biomass into biobased chemicals and fuel. At present, biofuran derivatives are generally obtained from cellulose and demicellulose fraction of biomass via the acid-catalyzed dehydration of their C6 and C5 sugar, and then converted into a wide range of products. Furfural is surely one of the two most used furan-based feedstock, since its chemical structure allows the preparation of various high-value added chemicals. Particularly, furfuryl alcohol is considered as one of the most important derivatives that serves as a precursor for the production of synthetic fibers, plastic, liquid fuel, lubricants, fine chemicals, and so on. Thus, in this work, we focused our attention on the selective hydrogenation of furfural into furfuryl alcohol, and this reaction is particularly interesting since under reductive conditions, several undesired reactions can occur, including the hydrogenation of furfuryl alcohol into tetrafurfuryl alcohol or its hydrogenolysis into methylfuran. The conversion of furfural into furfuryl alcohol was investigated by means of either hydrogenation or transfer hydrogenation processes. In a CTH reaction, H transfer reaction, the required hydrogen comes from hydrogen donor molecules, H donor molecules, used as reaction solvents such as primary or secondary alcohol, including isopropanol that can be considered the most widely used. In particular, in the CTH reaction, the use of an indirect H source allows to overcome the problem related to the use of hydrogen, such as safety and cost problem. And in this regard, a series of renewable and low-cost indirect H donor sources, such as methanol, ethanol, and isopropanol, have been investigated. All reactions were carried out in autoclave under batch condition at different reaction temperature by using isopropanol as H source and reaction solvent. The conversion of furfural increased by increasing the reaction temperature, and it was fully converted into furfuryl alcohol at 180 Celsius degree. And while either furfural conversion can be easily achieved in presence of molecular hydrogen as reducing agent, as expected. The hydrogenation of furfural was also investigated at different reaction time at 120 Celsius degree. As the reaction proceeded, in the presence of our catalyst, furfuryl alcohol yield progressively increasing, reaching after 6 hours the most complete conversion into furfuryl alcohol. And in order to evaluate the stability of our catalyst in the CTH reaction of furfural, a series of consecutive recycling tests were performed at 120 Celsius degree for 90 minutes. In this case, our catalyst demonstrated to maintain its catalytic activity after 5 consecutive reactions, and only slight change in furfuryl alcohol yield were found, highlighting the good stability of the catalyst that can be also directly recycled, simply washing with the isopropanol for the next reaction run. Therefore, in the light of the excellent performances of BM catalyst with the furfural as a starting substrate, we decided to extend the substrate scope to other biomass-derived aldehyde and ketones. Also in this case, good performances of catalysts were registered in the case of other carbonyl compounds such as HMF, benzaldehyde, acetophenone, and cycloethanol at 3 hours and in the temperature range of 120 and 118 Celsius degree. Next, we explored the conversion of furfural in pure alcoholic solvent, isopropanol, ethanol, and methanol in presence and in absence of added hydrogen. So in under hydrogenation, both under hydrogenation and transfer hydrogenation condition, with the aim to evaluate the solvent effect. And after 3 hours of reaction under CTH condition, a very low conversion, less of 5%, was registered with ethanol and methanol. As expected, while either conversion were achieved in presence of molecular hydrogen as a reducing agent for all investigated reaction solvent. So, in conclusion, we can say that spent lithium cobalt batteries were efficiently used as heterogeneous catalyst for the reductive upgrading of linear cellulosic derived molecules. Physicochemical characterization clearly indicated that after a thermal pretreatment, metallic cobalt and nickel species are present. BM catalyst demonstrate to be able to promote the selective hydrogenation of furfural into furfuryl alcohol under both hydrogenation and transfer hydrogenation condition. Recycling test in the transfer hydrogenation of furfural proved the boostability of our catalyst that can be directly recycled for the next reaction run. And finally, we also can say that BM catalyst can be successfully adopted as heterogeneous cobalt-based system for the hydrogenation of other carbonyl compound. So thank you for your kind attention, and see you live soon for all your question, curiosity, suggestion, and why not also for all your criticism. Enjoy the conference.
Thank you very much for this nice example of circular economy at its best. Is there any question for Emilia from the audience? Or if not, I have one actually. Did you experience any relation between the morphology or microstructure of your catalyst and the yield of your reaction, or anyway any influence on the conversion efficiency?
Okay. Thank you for thank you for your question. So the investigated catalyst, the physicochemical characterization of our catalyst reveals that the morphology is very heterogeneous. Is characterized by different oxides, such as aluminum oxide, nickel oxide, manganese oxide. But the main oxide are surely nickel, are cobalt and oxide, and nickel oxide and cobalt oxide. These results were confirmed by SEM EDX analysis and also by HEP analysis. But it's important to say that this analysis, this characterization reveals the presence of isolated oxide, and but really not there isn't a direct correlation between catalytic test and micro and macro structure of the oxide present in the structure of lithium spent lithium cobalt batteries, really. And we will surely investigate in time, in future time, these phenomena.
Okay, thank you. Is there any other question from the audience? No, if not, I have another one actually. Sorry, Emilia.
Thank you.
Just out of curiosity,
Yes.
you are working on recovering, recycling batteries, basically, no? So you are taking the devices and use it as catalyst for another application. Do you think there will be variability from one battery to the others in terms of the results that you can obtain?
Oh, sure. Battery is we have a difficult device to use it in this field. We are now working on another sample of similar spent lithium cobalt batteries with different composition of this oxide, probably also the catalytic test, the results of catalytic test probably will be different and with different performances. But we believe that cobalt species are always the principal, the main species that are responsible of the catalytic activity in our catalyst.
So there will be only a small fluctuation, you are saying?
Yes, of course.
Okay, I see. Thank you very much. I think if there is no question anymore, we can move further. Thank you very much, Emilia, for this nice presentation. And we go directly to the last speaker of this section, that is Roberto Fiorenza from Catania University. And he will present work titled Blue Kite Titanium Ceria Composites for the VOC oxidation and subsequent CO2 conversion into solar fuel.
Good afternoon. I am Roberto Fiorenza, a researcher in industrial chemistry at the University of Catania. In this work, I want to show you a fascinating approach to obtain the contemporaneous photothermocatalytic oxidation and the following carbon dioxide conversion into solar fuel. The photocatalysis is regarded as an artificial photosynthesis. It required the use of a semiconductor. The most used is the titanium dioxide, that when was irradiated by a suitable wavelength led to a promotion of an electron from the valence band to the conduction band, with the consequent formation of excited electrons in the conduction band and photoholes in the valence band. The interaction of this species with the oxygen and water led to the formation of radicals able to oxidize a lot of organic compounds, including the pollutants. Moreover, the excited electron can be used for the formation of hydrogen, or the excited electron together to the protons arising from the oxidation of water led to into the as called solar fuel, for example methane, methanol or carbon monoxide, that is important chemicals for the for a lot of product used in industrial chemistry. The less studied crystalline form of titanium dioxide is the Brookite phases, because it is very difficult to obtain as poor crystalline phases. But it possesses a moderate depth of photoelectron trap that make this crystalline phase suitable for the photoreduction reaction, as for example the water splitting or the carbon dioxide reduction. The interaction with titanium dioxide with the cerium oxide can be a promising strategy to improve the performance of titanium dioxide, because the cerium oxide possesses a lower band gap compared to titanium dioxide and thus improve the photocatalytic activity under solar light irradiation. It possesses redox properties that was activated by the temperature and so favored by a multi-catalytic approach as the photothermocatalysis. Moreover, it possesses empty 4F energy levels that favor the electron transfer and so improve the charge carrier separation. So the aim of the work is to study with an integrated approach the toluene photothermocatalytic oxidation and the further conversion of the obtained carbon dioxide into solar fuel. In our precedent work, we noted that the photothermocatalytic approach is the best one to favor the toluene chosen as model volatile organic compound total oxidation. And now we also study the further conversion of the obtained carbon dioxide into a valued added product. Moreover, to increase the performance, especially in the second reaction, that is the carbon dioxide reduction, we have added a small amount of bimetallic oxide as copper and cobalt oxide on the bruchite Syria composite. The presence of this co-catalyst can increase the amount of oxygen vacancies and can act also as electron storage relay system. For the carbon dioxide reduction, indeed, it is necessary the presence of two different co-catalysts. A reduction co-catalyst to produce photoelectrons, to increase the production of photoelectrons, and an oxidation co-catalyst for the formation of proton arising from the oxidation of water. The efficient coupling between electrons and proton can favor the formation of the solar fuel from the carbon dioxide. This is the experimental setup that we used for this integrated approach. So this is the first part, then the first reaction, that is the toluene photothermocatalytic oxidation. The obtained carbon dioxide was flowed in a second reactor where we used the same solar lamp used in the first reaction, and it was converted into carbon monoxide and methane that has the product in our experimental condition. The catalysts were prepared with the wetness impregnation, whereas the pure bruchite phases was prepared with, in collaboration with the University of Palermo, with the thermohydrolysis of titanium tetachlorides. Regarding the structural and morphological properties, the Raman spectroscopy is more sensitive compared to 2X-RAD to detect the bruchite phases. And the obtained spectra confirm the presence of only bruchite phases without the presence of anatase and rutile. Moreover, regarding the main vibrational peak, there is a blue shift of the main vibrational modes of bruchite due to the addition of the metal oxide particles. That is an indication of the formation of defect and oxygen vacancies due to of these species. The TEM imagings show the formation of a heterojunction between the bruchite titanium and the cerium oxide, whereas the added metal oxide particles are present as nanoxides. There is a decrease of surface area of bruchite titanium due to the addition of cerium oxide and nanoxide due to the thermal treatment necessary for the removal of the nitrate arising from the metal salt precursors. Regarding the optical properties, there is no variation in the band gap of the synthesized composites, whereas it is interesting to note the variation in the photoluminescent spectra, because the signal arising from titanium dioxide and cerium oxide were quenched due to the addition of the metal oxide species. And it is a further indication of the formation of defect as oxygen vacancies in the bruchite titanium cerium oxide lattice, with also an improvement in the charge carrier separation. Regarding the surface properties analyzed by XPS, there is a further confirmation of only the Brookate thesis, whereas there is a shift due to the interaction of the titanium and the cerium ions. A further shift was verified by the addition of the metal oxide species. Cobalt and copper are present as only 2 plus oxidation states, but it is very important to analyze that the concentration of the nanoxide added on the surface of the titanium cerium oxide is always 24 times higher than the nominal values. So there is an important surface segregation effect with these nanoxide that are present mainly in the surface of the sample. Regarding the photothermocatalytic activity in the toluene oxidation, we have noted in our precedent work that the photothermocatalytic approach is the best one for the total oxidation of toluene. And we have verified a further decrease of the temperature necessary for the 90% of toluene conversion into carbon dioxide with the addition of the contemporaneous addition of cobalt and copper on the surface of the Brookite Syria composites. This carbon dioxide was further converted in the second reactor, and if the second reaction was performed at the room temperature, the main product as the carbon monoxide and the bimetallic oxide sample is the best one. We have a further increase of the activity if also the second reaction was performed into photothermal approach with a methane enhancement that was higher of the carbon monoxide enhancement if we compare the result on the photocatalytic test at the room temperature and on the photothermocatalytic test. A further increase in the temperature of the second reaction increase also the formation of the solar fuel because the carbon dioxide reduction was favored. For this reaction, it is very important to study the surface height of the catalyst, and for this reason we performed the temperature programmed desorption measurement with carbon dioxide. On the best catalyst, it is possible to note different features that can be ascribed to the presence of both weak and very strong basic sites that favor the carbon dioxide interaction. Moreover, considering the temperature of the desorption peaks and the presence of a basic oxide as cerium oxide, it is possible to see the formation of bidentate carbonates that favor the conversion of carbon dioxide into carbon monoxide and after in the methane. The formation of this important intermediate was also verified by FTR spectroscopy. So different synergism can be exploited with these particular materials. The efficient heterojunction between Brookite and cerium allow to obtain an efficient photoelectron and photoholes separation. The presence on the surface of the cobalt and the copper oxide allow to obtain efficient co-catalysts that favor the carbon dioxide conversion and the water and the toluene oxidation. Moreover, there is a surface side synergism with the formation of carbonates that favor the conversion of the obtained carbon dioxide from toluene oxidation, and the increase of defect and oxygen vacancies due to the addition of these metal oxide species on the Brookite Syria composites allow is further conversion into solar fuel. So With these particular materials and this fascinating integrated approach, it is possible to exploit three different synergies: an energy synergism, a surface site synergism, and a bimetallic oxide synergism. Thank you so much for your attention.
Thank you very much for this interesting insight. Is there any question for Roberto from the audience? So I make one, if you don't mind. Did you try different percentage of copper oxide, cobalt oxide, and did you see any difference, or any difference in the way in which you deposit them, something like that? I think you have to unmute yourself.
Sorry. Yes.
That's okay.
The amount of the co-catalyst is very important to determine the final activity. But as we noted by XPS, there is an important segregation effect. So if we try to increase the loading of copper and cobalt oxide, there is an excessive surface coverage of the Brookite active sites, and it is detrimental for the photoactivity. So it is very important a very small amount of this, the addition of very small amount of this co-catalyst on the surface of titanium dioxide to avoid the occlusion of the sulfate side of titanium dioxide. We try only the impregnation methods until now, but maybe changing also the synthesis for the addition of these active species can be also another parameter that will be interesting to analyze.
Okay, thank you. Thank you very much. Is there any question arise in the meantime from the audience? If it's not, I would like to thank
you so much,
Roberto and all the speakers of the morning. And I will close now the session of this morning, and for leaving you to the well-deserved lunch break. And we will be back at 2 o'clock sharp for the afternoon one. Thank you all from my side, and see you later.
Good afternoon, everybody. Welcome to the second session of this very interesting meeting. We will have, I will be chairing the session until the coffee break. We have a series of very interesting talks today, this afternoon. Some of them, 4 of them, are pre-recorded contributions, so the author will be appearing at the end of the presentation, so as people can ask questions. I hope we will have plenty of questions. I know by experience that these online meetings has the strange paradox that nobody asks questions. I think we need to do that, otherwise the author feel kind of alone in the universe. So let's start with the first presentation. The first talk is from CNR, National Research Council, ICOM, Sesto Fiorentino. Sandra Doria will be presenting combined spectroscopic and theoretical approach to optimize the design of new organic triplet photosensitizers for multi-purpose applications. So please, let's start the presentation.
Good afternoon, everyone. My name is Sandra Doria, and I thank the organization committee of this Congress for having given me the opportunity to speak at this Congress. In this presentation, I will discuss about a class of organic compounds that act as triplet photosensitizers and that recently have attracted the attention of the physical chemistry research community because of their versatility and their very interesting applications in several fields. Triplet photosensitizers are organic compounds that can be efficiently excited to their triplet electronic state. Their ability to maintain a stable and efficient triplet excitation allows them to be employed in catalytic reactions as triplet energy donors. It is indeed well known that when a molecule absorbs energy, their singlet energy levels can be populated. Usually the relaxation to the ground state occurs via quantum mechanically allowed channels, resulting in fluorescence from the first singlet excited state. However, in some cases that we are going to discuss in the following slides, the transition to triplet states, namely intersystem crossing, that is not quantum mechanically favored, can occur, resulting in electronic population in triplet state that can then relax via different mechanisms that can be radiative or non-radiative and that can be exploited for several applications. Triplet photosensitizers can indeed be employed in multipurpose applications, some of them here summarized. For example, the phosphorescence due to radiative decay from the triplet state can be used for biomolecular sensing or bioimaging in living cells. The ability of triplet excitation to produce singlet oxygen can be employed for medical applications such as photodynamic therapy to fight tumors. In addition, long-lived triplet or long-lived charge transfer state are fundamental aspects that allow photosynthetic systems to transport the energy efficiently from the pigments that absorb the solar energy to the reaction center, where the conversion to the chemical energy occurs. So the possibility to reproduce these energy transport mechanisms in artificial systems is of great importance for light harvesting photovoltaic applications. In order to obtain a triplet photosensitizer suitable for the above-mentioned applications, some requirements must be satisfied. So, for example, the system must have a strong absorption in the UV visible region of the spectrum, an elevated efficiency of the intersystem crossing mechanism, and the triplet state must live long to avoid fast recombination. And finally, these kind of compounds must possess low toxicity. That is a needed requirement for medical applications. Several mechanisms can be employed to enhance the intersystem crossing efficiency that are based on the knowledge that spin change from singlet to triplet state must be compensated by orbital momentum change in order to guarantee the conservation of the total angular momentum. So this means that the spin-orbit coupling must be strong enough in these systems. An easy method to increase spin-orbit coupling is to use atoms with large atomic number, such as transition metal complexes, that unfortunately do not absorb enough in the UV visible region. So in order to obtain a compound with more intense absorption, a strategy is to realize the so-called intramolecular spin converter, where a light harvesting chromophore is attached to the coordination center. For example, here the energy is absorbed by a coumarin and then an electron transfer occurs that gives rise to a charge transfer state, which finally leads to triplet formation. The main drawback of these complexes remains a very high synthesis cost, a short triplet lifetime, and a very high toxicity, which make them not suitable for the mentioned biological applications, such as photodynamic therapy. So the main challenge is now to realize an heavy atom-free photosensitizer. This kind of photosensitizers can be obtained via different approaches, and a relatively new mechanism that in the last 10 years has received much attention and that is studied a lot in our group in Florence, is the intersystem crossing via charge recombination. That is a mechanism that has been observed in several bichromophoric systems under specific circumstances. In this case, we have a system consisting in a donor and an acceptor unit. Once the donor has been excited through visible excitation, an electron transfer between the two units results in a charge-separated state, from which a triplet state can be formed during the charge recombination process. This mechanism is responsible, was found to be responsible in literature for an efficient and fast formation of triplet states in many different kinds of systems. And furthermore, these triplet states can be long-living, up to 1 microseconds. The intersystem crossing via charge recombination can be mediated by different processes depending on the molecular design. So, for example, radical pair intersystem crossing is a phenomenon that occurs between distant chromophores that are rigidly linked. So, because of the long distance, the interactions are small and the hyperfine effect may be not negligible, and can favor triplet formation following these steps summarized in the equation. So first the donor is excited in its singlet state, then a charge transfer state is formed between donor and acceptor. This charge transfer state relaxes to a triplet state still with the charge transfer character, and then finally the acceptor is found in its triplet state. However, this kind of design is synthetically demanding and it has been replaced by the synthesis of close and orthogonal chromophores. So due to the orthogonality, the dipole coupling is suppressed and the spin momentum change can occur via orbital momentum with orbital momentum compensation, starting as well from a charge transfer state. So for this reason, this mechanism is called spin orbit charge transfer intersystem crossing. In the following slides, I will present some examples of this mechanism observed and studied by our spectroscopy group in Florence. In this work, we study a body P unit linked to a perilene. So following laser pulse excitation in the visible region, a charge transfer state is formed that can relax to the perilene triplet via this spin-orbit charge transfer intersystem crossing mechanism. This mechanism strongly depends on the polarity of the surrounding environment. Indeed, in this case, the solvent polarity affects the energy of the intermediate charge transfer state, and the intersystem crossing is allowed only in non-polar solvents. The behavior of this compound can be investigated by a number of experimental techniques that give a complete picture of the sample electronic properties. Indeed, for example, stationary and ultrafast spectroscopy performed in the nanosecond and picosecond timescales can give important pieces of information on the energetic channels and the energy and the states, electronic states involved in this triplet activation process. Furthermore, the different species present at different times following the excitation, for example, the anions and cations due to charge separation, can be recognized from specific spectral feature in these experiments. In this other work, the triplet state of perilene is observed as well when perilene is linked to a naphthalimide diode that was studied also in this case as a function of solvent polarity. Here we found an efficient triplet state formation in a particular configuration where the relative angle between donor and acceptor is actually 72 degrees. So this result proves that there are different electronic aspects that play a role in this triplet behavior, and the orthogonality between donor and acceptor may be not strictly required. In this additional example, the same donor, a naphthalene mide, is linked to a rhodamine unit, and this spin-orbit charge transfer mechanism was found to be responsible for the formation of a triplet state with charge transfer character, leaving almost 1 microsecond. This is very important. This result is of particular interest when considering photovoltaic applications, where this kind of long-lived charge transfer state can play an important role for efficient energy redistribution and conversion in photovoltaic devices. In some cases, triplet activation via spin-orbit charge transfer mechanism is observed in systems made of identical molecular units that are placed closed and orthogonal. The presence of intersystem crossing in this case implies a symmetry breaking process in the establishment of the interaction between the two units because they are identical and orthogonal. In this work, we have indeed observed a triplet formation in case of a two-body bisystem in perpendicular conformation, while this channel of triplet activation is not activated in case of non-orthogonal configuration. So as a summary, I would like to highlight the great application potential of organic triplet photosensitizers that, however, must satisfy strict requirements in terms of energy level matching, geometry, biological compatibility. So the optimization of the design and synthesis of these compounds is still another problem, mostly because the relation between the chemical structure and the electronic behavior is not fully understood, and thus the prediction of the triplet efficiency is not trivial. The best way to achieve the knowledge necessary to the realization of the best, of an optimum triplet photosensitizer is to employ different theoretical and experimental techniques in order to obtain a complete picture of the compound behavior. In the end, I would like to thank you all for the attention and to thank the ultrafast spectroscopy group at Lens in Florence that carried out most of the research that I presented today and where many CNR researchers currently works. Thank you very much.
So thank you very much for the very interesting talk. We have time for one question because of time limitations. Is there anyone who would like asking a question? Please. Come on.
Actually, this is Giacomo from Perugia. Thank you very much for a very, very nice and very clear talk. Actually, the very last slide you mentioned theoretical approaches that you should use to improve the description of your system. So I wonder if you already have theoretical results, and in case, which kind of results are DFT, DDFT, or what else?
Yeah, so actually I work in an ultra-fast spectroscopy group, so in my group we are pretty experimentalists, but we have some collaborations with other universities, so we work, yes, in collaboration to perform like DFT calculations. Yes, fundamentally the main issue is to be able to match the electronic state, the energetic levels of donor and acceptor. So in this case, the theoretical approach can be very, very useful.
Yeah, sure, that makes sense. Okay, thank you very much. Thank you.
Thank you.
Anyone else? I would have some question to ask, so I take advantage of my position to ask you a question, even though we have not much time. And very short, could you have any chance to verify the charge separation state formation by spectral electrochemical approach?
Yes, yes.
Electrochemically and so.
Yes, we have also some collaborations. So in almost all the research that I presented, we had the possibility to verify also the presence of anions and cations of the species through yes, electrochemistry.
Okay, great. Thank you very much.
Thank you.
And thank you again. And so we will pass to the next talk. Thank you very much. And so Leonardo Duranti, University of Rome, Tor Vergata, smart composite electrode for reversible solid oxide cells. So please start the pre-recorded presentation.
Hello everybody, I am Leonardo Duranti, Research Fellow in the Department of Chemical Sciences and Technologies at the University of Rome, Tor Vergata. First, I'd like to thank the organizing committee for giving me the opportunity to show you this presentation. My research activity is focused on the design, development, and testing of ceramic materials for energy production. Now, I will share my screen. Okay. Today, I'm going to present my latest results, the development of a versatile, long-lasting, and fuel-flexible electrode material for reversible solid oxide cells. I will go through these few points, starting from how solid oxide cells, both electrolyzers and fuel cells, represent one of the most promising ways to draw as much energy as possible out of renewable sources, becoming efficient and reliable devices for the upcoming energy transition. Then, I will describe the cell compartment on which I focused my research, the fuel electrode, describing the state-of-the-art materials and some of the open issues regarding their application on large-scale systems. Finally, I will present you the innovative composite I have been recently working on, its main features and application as an anode for solid oxide fuel cells fed with different fuels, as a cathode for CO2 reduction in solid oxide electrolyzers, and in general, as a fuel electrode for reversible cells that can interchangeably operate between fuel cell mode and electrolyzer mode. Let's start by saying that last year, the outbreak of COVID-19 pandemic lowered the electrical energy demand all over the world as a consequence of movement restrictions. Italy lived one of the worst scenarios, and its demand was pushed down by over 25%, as you can see in this graph. Nevertheless, here you can see the share of energy coming from renewable sources in the Italian electricity demand. The increasing trend compared to data from previous years seemed not to be affected at all by lockdown measures. The reason for this is to be found in the way this kind of energy is provided to the final users. Long-term contracts and support policies from the governments give this technology a must-run status and make the energy cost less variable. So renewables represent indeed a reliable and resilient energy system, but still their intermittency prevents them from becoming a major source of energy. Efficient storage would ensure continuity of supply. Here is a scheme of pretty much all the existing storage technologies with their positive and negative aspects. Among them, converting excess energy into chemicals seems to be the best option in terms of high energy density, ease of handling and transportation, and also long-term storage. Solid oxide cells are multi-layered ceramic devices that operate at high temperature. A dense electrolyte separates the two electrodes, where the oxidation and reduction reactions take place. Here on the left, a solid oxide electrolyzer converts excess energy into valuable chemicals. Compared to low-temperature electrolysis, solid oxide electrolyzers ensure unrivaled conversion efficiencies as a result of favorable thermodynamics and kinetics at higher operating temperatures. The obtained fuel can be efficiently converted back into electrical energy using a similar device in fuel cell mode, and then power the grid. The overall efficiency level would increase again if both power-to-gas and gas-to-power processes were performed by the same device, introducing the concept of a reversible solid oxide cell. The challenge here is finding multi-purpose materials that can withstand exposure to extremely different environments and being at the same time catalytically active for various reactions. For example, if the material chosen to fabricate the fuel electrode is able to process carbon-containing fuels, Carbon dioxide storage is pretty easy in fuel cell mode, as you can see on the right. Stored CO2 can be then reduced in electrolysis mode on the left, alone or together with water, to produce carbon monoxide, syngas, and molecular oxygen. So basically, this presentation will be about the development of a fuel electrode material, which will have to be as versatile as possible to ensure high-level operation in different conditions. Nickel-based composites like nickel and yttrium-stabilized zirconia represent the state-of-the-art for this cell compartment. Nickel has unrivaled abilities to oxidize fuel in fuel cell mode and also to promote water and CO2 reduction in electrolysis mode. Nevertheless, these electrodes suffer from crucial drawbacks that contribute to slow down the large commercialization of this technology. For example, nickel does not allow for fuel flexibility. In fact, when hydrocarbon-based fuels are used in fuel cell mode, nickel catalyzes residual carbon deposition, resulting in cell deactivation. Electrode degradation is also common in electrolysis mode, especially at high current densities. So I decided to design an innovative electrode based on complex oxides, which would be able to exploit the catalytic ability of nickel without triggering carbon deposition to finally obtain a multitasking and fuel-flexible device. I basically used a perovskite oxide containing iron within its structure. When fuel is fluxed at the electrode, it creates a highly reducing environment. And the structure of this perovskite that you can see on the XRD panel on the left undergoes a phase transition. These leads to the segregation of iron nanoparticles on the oxide surface, as you can see from the transmission electron microscopy analysis reported here on the right panel. To complete the electrode composite material, I added another oxide, a fluoride structure this time, samarium-doped ceria with a low percentage of nickel oxide supported on it. So after reduction, the perovskite, the blue XRD profile on the right, produced metallic iron. The fluoride, the green XRD profile, showed metallic nickel. When the two oxides were closely mixed, an iron-nickel alloy was formed upon reduction, as you can see in the red XRD profile. This alloy was again spotted on the catalyst surface, and its nature was confirmed thanks to nanobeam electron diffraction analysis. In this way, I obtained metal nanoparticles evenly distributed on top of an oxide substrate. These nanoparticles are catalytically active towards fuel oxidation, so they are useful when the cell is operated in fuel cell mode. Iron-nickel alloy is also reported to have high catalytic activity towards carbon dioxide reduction. Moreover, the presence of iron should in principle mitigate nickel tendency to catalyze carbon deposition. Here is the ultimate cell design. The new fuel electrode is on top of a commercial ionic conductor used as electrolyte, and another commercial mixture used as the opposite electrode, which has to perform oxygen reduction in fuel cell mode and oxygen evolution in electrolysis mode. Such a device was tested starting as a fuel cell operating in hydrogen. Its behavior in a highly reducing environment introduced by hydrogen was evaluated. A power density of 657 milliwatt per square centimeters and a low polarization resistance were obtained at 850 degrees Celsius. Most importantly, the fuel electrode showed remarkable redox resistance. The cell was set at a fixed voltage and the current density output was measured in hydrogen. Overnight, the cell was kept in an inert atmosphere for the first 3 cycles, and then in a highly oxidizing atmosphere when air was fluxed in the last 2 cycles. No major degradation or deactivation were observed after 120 hours, and the current stabilized after an initial decay. The current density loss that occurred within the first 3 cycles is believed to be due to the commercial electrolyte degradation, since no polarization resistance increase was witnessed at the end of the test. Finally, the cell was tested in methane, and surprisingly, upon gas switching, a higher power density than the one obtained in hydrogen at the same temperature was observed, showing that this composite has indeed high catalytic activity towards methane oxidation. These results were also higher compared to systems with a similar cell architecture tested in the same condition and recently reported, as you can see on the right panel. Cell endurance was tested again in methane to prove the fuel electrode tolerance towards carbon deposition. The open circuit voltage was monitored at 850 degrees Celsius under methane flux for over 120 hours. No deactivation was observed, and cell resistance was confirmed by Raman in situ analysis performed after the test. Negligible traces of sp2 hybridized carbon were found, as a low G band is visible in the after-test spectrum on the right. So basically, when the cell is working in methane, the iron-nickel alloy activates methane, and the carbon deposition is slowed down by the presence of iron, and also thanks to the high permeability of the fuel electrode to oxide ions coming from the electrolyte that are able to oxidize any deposited carbon. Up to now, we saw that the composite material proved to be resistant to redox conditions and carbon-containing gases in fuel cell mode. Using exactly the same cell configuration, several gas mixtures with different carbon dioxide to carbon monoxide ratios were fed at the fuel electrode, and the cell was tested in electrolysis mode. The composite electrode showed remarkably high activity for CO2 reduction, reaching the highest current density of 2.66 ampere per square centimeters at 2 volts in a 95:5 carbon dioxide to carbon monoxide ratio. Usually, in electrolysis mode, carbon monoxide is mixed to carbon dioxide to prevent the electrode from reoxidation. But this material showed high activity also in pure CO2, reaching 2.43 ampere per square centimeters at 2 volts. The whole device showed high stability as an electrolyzer too. It was tested in a 95:5 CO2 to CO gas mixture, both in the short term, varying the potential from 1.3 to 1.9 volts and showing stable response, and in the longer term, fixing the voltage to 1.35 volts. The cell provided more than 1 ampere per square centimeter for more than 40 hours. The slight performance degradation observed after 45 hours was mainly due to the formation of strontium carbonate, as highlighted by the after-test Raman spectroscopy analysis performed in situ and showed on the right panel. Okay, on the other hand, since carbon monoxide is a fuel, increasing the amount of CO, the device showed again to be remarkably active as a fuel cell running on carbon monoxide, reaching 485 milliwatt per square centimeter of power density when CO was the 70% of the gas mixture. Cell behavior was perfectly reversible for intermediate CO2 to CO compositions, showing very low polarization resistance values at open circuit. Basically here, the cell can be operated in both modes, keeping the same gas feed. Now, picking a commonly reported mixture, 70% CO2 and 30% CO, the obtained polarization resistance at open circuit voltage was lower than recently published values. Of course, these values came from similar systems tested in the same conditions. And you can see that are reported on the histogram on the right. Okay, so to conclude, an innovative smart composite material was developed as a multifunctional material for the fuel electrode of solid oxide cells. The composite material showed the formation of a nickel-iron alloy in operando conditions. The electrode showed high performance and versatile activity in fuel cell mode for hydrogen, methane, and carbon monoxide oxidation, proving also to be resistant to redox cycles and carbon deposition. As a cathode of a solid oxide electrolyzer, this composite provided more than 2.5 ampere per square centimeters at 2 volts, keeping a current density output of over 1 ampere per square centimeter for over 40 hours, with remarkably low polarization resistance values. Okay, that is the end of it. I'd like to thank Professor Elisabetta Di Bartolomeo, all my colleagues and collaborators that contributed to the research project, and of course, all of you for your kind attention. Thank you.
Thank you very much. Thank you very much, Leonardo.
Thank you.
So the presentation is now high to see you. The contribution is open to discussion. Do you have any question? We don't have much time. 1, 2 questions at most. Please. Who's asking the first question? No? Very interesting presentation, very interesting system. I will start asking my own question now.
Yeah.
Very naive one. So the strength of your system apparently is the fact that you are producing in situ a nickel iron alloy.
Yeah.
So very naive question. What's the advantage of preparing that in situ compared to starting with the alloy since the beginning?
Yeah, sure. Thank you for your question. It's a very interesting one. The thing is that, okay, can you hear me? I think, yeah,
Sure.
okay. The thing is that usually these kind of catalysts are prepared supporting metal from solution casting, for example, on an oxide substrate. I should prepare something like a mixed solution with precursors like iron nitrides or nickel nitrides and then dropping it onto an oxide substrate. This would result in a higher percentage of metal, but usually this kind of preparation leads to not evenly distributed particles, which usually have size from up to I mean, bigger than 1 micron, and while in this case exploiting the supported nickel on one oxide, which is only the 30% of the whole composite, so the nickel percentage is only the 2% of the whole composite, and exploiting iron egg solution, I managed to have a well-distributed, firmly attached nanoparticles onto the oxide substrate. Moreover, this kind of trick that the perovskite does, so the exsolution in the reducing conditions and the reoxidation tends to be reversible. So a huge part of iron is reintegrated into the oxide. Of course, I noticed indeed I noticed the presence of some nickel iron oxides after the reoxidation, but the major 99% of the oxide structure was recovered. So if the catalyst gets poisoned, it's easy to recover in this way.
Okay.
I mean,
that's something I missed from your presentation. Sorry.
Yeah.
Thank you very much. Any other question, please? Okay. Everybody's happy with your presentation. So thank you very much. And
thank you so much.
Move on. Thank you. Bye. And so let's move to the next speaker, Alessandro Cingolani from the University of Genoa. Electrospinning as a tool for preparing rare earth doped shear nanofibers to be used in solid oxide cells. Okay.
Hello everybody. Today I'm going to talk about my master thesis work that I'm currently doing in the University of Genoa in physics chemistry section, that is based on the electrospinning as a tool for preparing rare earth doped shear nanofibers to be used in solid oxide fuel cells. We start with an outline. So we have the motivation of the project, of course. Then we have an introduction of the rare earth doped shear. We will see also the electrospinning instrument description and the sample preparation with the parameters optimization. Then we will have also the characterization obtained by the electron microscopy and microraman analysis, and we will conclude with the future perspective of this work. Motivation are really quite simple. Rare earth doped shear are widely studied as electrolyte in solid oxide fuel cells because of the high value of ionic conductivity in a range of temperature that goes from 673 Kelvin to 973 Kelvin. But this low operating temperature of these fuel cells has advantages and disadvantages, of course. One of the advantages is that the intermediate temperature slows down the degradation process of the cell. But the main disadvantage of this low temperature, operating temperature, is that also we, of course, lower the cell performance. This is because we have lower electrokinetics. So it is necessary to improve the electrode architecture, for example, by maximizing the surface area of the electrode itself. In order, for example, to extend the three-phase boundary, this phase is a phase in which electrons, ions, and gases meet each other, and when the reaction of the fuel cell take place. An important tool we can improve the architecture of the electrode is, for example, the electrospinning. That is a quite innovative technique to synthesize nanofibers that have to be used for electrodes. So, before talking about the electrospinning, I would just introduce you the rare earth doped serial systems. In this case, this cerium 1 - X, rare earth X, oxygen 2 - X 2 can be obtained really simply by doping the cerium oxide, so cerium oxygen 2, with a trivalent rare earth ion. We have to dope this material because the ceria itself, so the cerium oxide, is not an ion conductor. But with the doping process, we can have the formation of the oxygen vacancies in the crystal lattice. Of course, in order to obtain, or to maintain, let's say, the charge neutrality of the structure. What happens is that the doped system is an ion conductor, and its ionic conductivity is strictly correlated to the crystalline structure. We can have different kinds of structures. So we can have the fluoridic, that is indicated with the letter F, that has spacecraft that is Fm-3m. It is a cubic structure with the coordination number that is 8, as you can see in this image. And then there is also another structure of this ceria, that is the cubic structure indicated with the letter C. That is, again, a cubic structure, but with the coordination number 6, as you can see, the octaedra here. The difference between these two structures is that the C structure is a superstructure of the F structure. We can now introduce the electrospinning technique. So then, electrospinning process is a really innovative technique in which an electric field force is applied on a fluid whose flow is controlled by a pump. So generally, the electric force ranges between a value of 10 to up to 30 or even something more kilovolts. So what happens is that when the force of the electric fields overcome the surface tension of the solution that it exits from the needle of the siren, a Taylor cone is formed at the exit of the needle. And from this Taylor cone, so from this thin cone, nanofibers are elongated and they deposit on a collector. So this is the collector in which we deposit the nanofibers. In this case, this image is a vertical electrospinning. This kind is an horizontal. This again is another kind of electrospinning with the siren is an horizontal position, but the needle is in a vertical position. What we can see is a focus, a zoom on the Taylor cone, and this is the beginning of the elongation of the nanofiber. Then the nanofibers assume this circular and spiral motion, and they deposit on the flat collector in this case. We can also have cylindrical collectors, for example, that can rotate. And generally, this is the fiber mat that we obtain at the end of the synthesis procedure. One of the most important parameters that we have to consider is the diameter. The diameter of the nanofiber is one of the main aspects that we have to control during the synthesis of these nanofibers. because for solid oxide fuel cell, the nanofiber diameters play an important role in determining the performance of the system. So we have to optimize a lot of parameters in order to obtain a good range of diameter of our nanofibers. Generally, the diameter of the nanofiber is between 150 and 220, 250 nanometers. So what we have to optimize, of course, is the solution that we inject in the instrument. Then we have to optimize the value of the applied voltage. And of course, the flux of the solution. And then the distance between the needle and the collector and the humidity. So the solution is really simple to prepare. So is obtained by mixing the nitrates of cerium gadolinium and also samarium in the case of the double dop system in a solution of water and ethanol, 2 parts of water and 1 part of ethanol. And then after the magnetic mixing on a stirrer, we can add the polymer to the solution because we need a viscous solution, a polymeric solution. In this case, we use PVP. In the table, you can see the amount, so the masses weighted for a sample that is the gadolinium doped series 15. As you can see here, we can have 2 parts of water, 1 part of ethanol, then the polymer, and then the nitrates. Once the solution is optimized, we have also to optimize the parameters, the experimental parameters of the instrument, so the electrospinning. In this case, we can see voltage and flux. After a lot of synthesis, we just found that the base value of voltage for the elongation of the CDC nanofibers is around 21 kilovolts. And the flux of the exit of the viscous fluid from the sine is 1 milliliter per hour. So the process is very slow, but then the nanofibers obtained are really nice and good. Then we have also to consider the distance between the needle and collector and the humidity of the system. So the distance between the needle collector plays a really important role on the diameter of the nanofibers. And we just find out that also in literature, the distance that is 10 centimeters is one of the best that we can use in order to obtain a nanofiber diameter between 150 and 220 nanometers. Then we also have to consider the humidity. The experimental humidity is set at 32%, and this because if the humidity is high, so a value around 60% or even more, what happens is that the water, of course in the air, is absorbed by the fiber mat that goes back to a jelly status. This is quite weird because we have, of course, to resynthesize all the mat because it's a reversible process. Now, so we can see a SEM analysis of 2 samples. In this case, we have
avere accesso allo spettrofotometro che oggi è occupato
the gadolinium doped series 15. So the 10 is on the left and the 15 is on the right. As you can see, the nanofibers obtained seems to be thin. We have now the measurement about the diameter. And in this case, also for the ZDC15, we can also see a partial orientation of these fibers going up to the right. Now we can see other 2 images of this. This system is a double dop system, so we have gadolinium and samarium cerium oxide in this case. So gadolinium, there is the GS samarium C cerium 10 and 15. As you can see, also for this kind of systems, we obtain a nice fibrous mat where the fiber seems to be thin, and we also here we have to collect the average diameter. I will show you now a Raman analysis. As you can see here, there is the peak of the stretching between the oxygen and cerium bond in coordination 6, and the analysis are room temperature analysis, that is the red line, and also temperature analysis, in which we have 300, 400, 500, 600, 700, and 800 degrees Celsius analysis. What we can see is that with the increase of the temperature, of course, the Raman shift decrease, and is logic because we need less energy to excite the sample with the increase of the temperature. And another thing that we can also see is that we have the sample is not modified by the increase of the temperature, and this is really important because the fuel cell works around between 600 and 800 degrees Celsius. So if the sample modifies that in this temperature, this could be really bad for the efficiency of the fuel cell. So what we see is that the sample is stable. This case is GDC10 sample. So now the future perspectives. The work is currently going on. This is my master's thesis, as I told before. We have to accrue the experimental diffractograms at the electrosynchrotron, and we have also to refine, I have to refine with the Riemann method all the parameters. And all the refined parameters will be compared to the same refined parameter of the bulk samples. And then I also have to assemble the symmetrical cell with the fibrous electrodes and test. So I do electrochemical test in order to see if the performances of the cell that have the fibrous cathodes, for example, are better than the standard system used. And we think that it would be like this, so that they will have a better performances. So after this, I just want to thank you for your attention and just have a good day off.
Okay, thank you very much, Alessandro. So the contribution is open for discussion. Any question? Hi.
Hello, everybody. Thank you.
Come on. Any question? So Alessandro will ask you a question, very simple.
Yes.
Again, naive question concerning the electrospinning procedure you're using. How flexible is it in terms of composition of the fibers that you use? Can you easily modify and control the composition of your fibers?
Yes. It's kind of very easy things to do, also because you have to prepare the solution that you have to inject with the instrument, with the sighting instrument. So you can prepare different kind of solution with different composition and obtain different math of fiber with different composition. We synthesize six different composition between the single dope and the double dope Syria system. So it's quite easy. The electrospinning is a really interesting tool also for this reason. Yeah.
Okay, thanks. And is it a unique fiber, or you have some average length? And how important is the length of the fibers in that case?
Okay, tendentially, it is a unique fiber that elongates, but sometimes the procedure, of course, is interrupted with some fluctuation of something. You know, there is a high voltage applied, or if we have to clean the needle, so we have to switch off the voltage, clean the needle, and then restart the process. So
start again.
But the most important thing is not the length, but the diameter of the fiber in this application. Yeah, the perfect diameter is around 100 nanometers. So that's the most important parameter that we have to check.
Yeah, that was clear from your presentation. Okay, thank you very much. So if there is no other question, I thank you again, and let's go on. Thank you. And next talk will be Silvia Mauri from IOM National Research Council in Trieste, towards the understanding of the direct methane to methanol reaction mechanism catalyzed by Syria copper oxide nanomaterial and operando NEXAF's study. Please.
Good afternoon, I'm Silvia Mauri, and today in this presentation I will show you the main results of the research I'm conducting as a PhD student of the University of Trieste. My PhD is focused on the application of the operando ambient pressure NEXAF technique with the soft X-rays, of which my supervisor Piero Torelli spoke extensively this morning. So briefly, at the high energy beamline at the Electrosynchrotron of Trieste, it's possible through an innovative setup to acquire absorption spectra at ambient pressure continuously, using the synchrotron radiation as a soft X-ray source. We can also inject gas mixtures inside the reaction cell in order to follow the absorption spectra evolution consequent to an interaction between the gases and the sample surface. In this optic, the technique is perfect in order to investigate the mechanism of catalytic reactions, also because the reaction cell is directly connected to a micro-GC, so we can detect the gas products while acquiring the absorption spectra. So I exploited this technique in order to investigate a catalytic reaction that up to now is considered as a dream reaction, that is the direct methane to methanol. Indeed, it allows to directly convert the methane, a greenhouse gas, into a portable liquid fuel such as the methanol. The problem is that a catalyst able to give good methanol selectivities is difficult to design, given the fact that the catalytic mechanism behind the reaction is still not completely understood. So I chose as a starting point for my study a recent article in which the author synthesized a model system based on cerium oxide deposited on a copper 111 single crystal. This catalyst gave good methanol selectivity at low temperatures and at ambient pressure. Moreover, they found out that water improved drastically the catalytic performance, and they attributed the catalyst efficiency to the monolayer of copper 1 oxide that forms at the interface between the ceria and the copper during the synthesis. The weak part of the study was the synthesis method, since it was not suitable for large-scale applications. So we tried to synthesize two similar cerium oxide and copper oxide-based samples, which will be shown later. But for both samples, we measured the copper L23 and the cerium M45 edges, trying to reproduce the experimental condition of the article I showed before. So the experiment involves 3 initial steps, in which the sample is cleaned and activated at 300 Celsius degrees. Then, at lower temperatures, methane is injected in the reaction cell for 1 hour. After that, the oxidizing agent, in our case the oxygen, is added to the reaction mixture. And after 20 minutes, the oxygen is removed, keeping only the methane, in order to evaluate the reversibility of the surface modifications. So, as I said before, we synthesized 2 samples. The first one was a model system synthesized using a pulsed laser deposition method. And in this way, we tried to reproduce the system used in the article that inspired this study. The second sample was prepared in collaboration with the University of Udine through a more scalable milling method. So now I will show you the results obtained for the first model system. This figure shows from the bottom to the top the spectral modifications of the copper L3 edge during the reaction at 170 Celsius degrees. So in the bottom part of the figure, I reported the reference spectra of the copper 2 oxide, the copper 1 oxide, and the metallic copper that we acquired on the beamline. So in the first spectrum, acquiring helium, the black one, we can observe that the copper appears mainly as metallic, even if some sites are present in a +1 oxidation state. By introducing the methane and water, the spectra are unchanged. When the sample is exposed also to oxygen, the copper is oxidized to copper 1 oxide, as you can see from these 2 spectra. When we removed the oxygen and the water, keeping only the methane, the spectra changed radically, indicating a copper reduction to metallic copper, as you can see from this purple spectrum. This result showed an important reactivity of the copper 1 towards the methane. During the same reaction, we followed also the behavior of the cerium M45 edges. As before, I reported the references of the cerium 3+ oxide and cerium 4+ oxide. In this case, before introducing the gases, we started with a mixture of cerium 3+ structures A and B and cerium 4+ structure C. Also in this case, the spectra are unchanged after we expose the sample to methane and water. When also oxygen is introduced, you can observe a weak decreasing in the intensity of the structures A and B, indicating an oxidation of the ceria. This oxidation is irreversible, as you can see from the last brown spectrum. But let's move now to results obtained with the milled sample. So here I reported also a slide regarding the sample activation, since we observed an interesting behavior. The figure on the left shows the evolution of the copper L2 and L3 edges during the heating in helium. You can observe even better from the picture on the right, that is only a zoom on the copper L3 edge, that with the heating we observe a weak reduction of the copper from copper 2 to copper 1, that is this structure. Looking at the cerium M4 and M5 edges, you can see that at room temperature, the cerium has a prevalent 4+ oxidation state, but also some cerium sites are present as small shoulders. By heating, the shoulders disappear, indicating an oxidation from cerium 3+ to cerium 4+. In this way, we understood that the catalyst activation involved a redox behavior between the copper and the ceria. But let's see now what happens during the reaction. So from the bottom to the top of this figure, you can observe that when the sample is exposed to methane, the copper changes its oxidation state from copper 2 to copper 1. Moreover, you can observe that the copper 1 evolves over time, suggesting some rearrangement of the sample structure during the interaction with the methane. When also oxygen is added to the reaction mixture, copper 1 is totally oxidized to copper 2, indicating a complete reversibility to the starting conditions, as you can see from this blue spectrum. This cycle can be repeated more times, obtaining the same result. Looking at the cerium edges, we didn't observe any spectral modification during the reaction, so the cerium maintains its 4+ oxidation state during all the reaction steps. As I said before, we monitored also the gas products through the online micro-GC only for the milled sample. We observed that the main reaction products were carbon dioxide and water, which are the main products deriving from the total oxidation of the methane. But we detected also the presence of small amounts of formaldehyde and methanol. So it means that we managed to obtain the NTM reaction. So based on the obtained results, we tried to predict a mechanism model for both the samples. For what concerns the PLD model system, the mechanism involves the methane activation through a reactive oxygen located at the interface between the ceria and the copper. The methane activation takes to the formation of a methoxy group and an adsorbed hydrogen, and introducing the oxidizing agent, the methanol is produced. This mechanism was confirmed also by a further study by Rodriguez, published recently in 2020. For the milled sample, the reactive interfacial oxygen activates the methane differently, taken to a methoxy group adsorbed on the ceria, while an hydrogen atom is adsorbed on the reactive oxygen. The oxidizing agent also in this case allows the methanol desorption and restoring of the initial situation. We are now performing also some theoretical calculations in order to confirm these predictions. So, concluding, for the model system, we observed an important copper oxidation during the exposure to the oxygen, and we detected also a strong interaction between the copper 1 sites and the methane. For what concerns the cerium 3+ sites oxidize to cerium 4+ during the exposure to oxygen in an irreversible way. For the milled samples, we followed the sample activation with a simultaneous copper reduction and cerium oxidation by heating. During the exposition to methane, the copper reduces from copper 2 to copper 1, and the starting point is restored just by introducing the oxygen, indicating the easy regeneration of the catalyst. We observed through the micro-GC the products deriving from the total methane oxidation, which are carbon dioxide and water, and from the partial oxidation, so formaldehyde and methanol. And these results confirm that this catalyst is able to perform the DMTM reaction. No modifications were detected at the cerium M45 edges during the reaction. So first of all, I want to thank my supervisor, Dr. Piero Torelli, then Luca Braglia, who helped me with all the measurements. Then I also wanted to thank Pasquale Orgiani and Sadip Chalouadi, who provided me the sample synthesized with the PLD. And finally, our collaborators from Università degli Studi di Udine, who performed the synthesis with the milling method. And thank you for your kind attention, and I'm here for your questions.
Okay, thank you very much, Silvia. Very interesting talk, and exactly in time. And so there is plenty of time for asking questions now, so no excuse. Please, who's first? Everything was so clear, so well presented, so no questions. Are you sure? No question? So I would like to ask you a very concerning the fact, I was impressed by the fact that you have this irreversible Syria oxidation at some time in the presence of oxygen that is somehow explained. My question was initially to ask you why, see if you have some explanation, but you explained that. And so the question changes a little. How critical is the fact that the Syria is irreversibly oxidized for the performance of your material, your catalyst?
So the irreversible oxidation occurred in the sample synthesized with the PLD, and it was, yes, a bit critical because with that sample it was not possible to repeat the oxidation of the methane again. So the initial conditions were not restored. While in the sample synthesized,
so there is no way to recover.
No.
No way to recover the material.
No, with that sample. While in the other sample, yes. But in the milled sample, there was no oxidation of the cereal. So this is a good point for the milled sample.
Okay, so a good point for choosing the right technique to produce material. Thank you very much. So someone would like to ask any question? No? So let's go on. Thank you again very much for your very interesting presentation. And let's move to the last talk. This time is live. Marco Piccini from IIT University of Genoa, titled Synthesis and Water Dispersion of Nickel Iron Layered Double Hydroxides for Energy Storage Applications. Okay, Marco, please.
Okay, can you see the presentation?
Sure.
Now can you see it in full screen?
Okay.
Okay, so hello everybody, I'm Marco Piccini, and I'm a PhD student at the University of Genoa, and I work in IIT in collaboration with bidimensional SPA. So I am now talking about nickel iron layered double hydroxide. So the first question to answer, the first question to answer is what are layered double hydroxides? So the crystal structure of layered double hydroxides arise from divalent metal hydroxides when you put this X coefficient equal to 0. Layered metal hydroxide are made by the stacking of layers of hydroxide made by octahedrons, at which vertex are placed a hydroxide group, and at the center of each octahedron there is a metal cation. So when some divalent metal cations are substituted by trivalent metal cations, the hydrox layer gain a certain amount of positive charge that must be neutralized by the presence of anions in the interlayer space alongside with water molecules. So layered double hydroxide naturally occur as minerals, and these minerals currently have many applications as anion exchange for concrete and flame retardant, and in oil industry as steam reformer. Nowadays are under investigation layered double hydroxides, or LDH, I will call LDH for now, based on transition metals for their catalytic application in water splitting and other electrocatalytic or photocatalytic application, alongside with some medical application. So let's start about talking of nickel iron LDH. The standard procedure to synthesize nickel iron LDH is the urea hydrolysis synthesis. Is basically an aqueous solution which turns alkaline as a result of urea hydrolysis, which releases ammonia and carbonate anions. In this condition, the iron hydroxide in amorphous form reacts with nickel ion dissolved, forming the LDH. These standard procedures can be easily achieved under ambient pressure and 100 degrees, but we observed that after the synthesis, the obtained product, if treated with sodium acetate, can easily be dispersed, and this dispersion is stable for months in ethanol. So we thought that the key to obtain stable dispersion in low boiling point solvents, as ethanol or water, are carboxylate anions. So we started to develop our synthetic method, which is based on metal citride polymers. So how this method works is similar to the previous one, but uses 3-sodium citrate as a chelating agent and sodium hydroxide to rise the pH of the solution, and is also achieved at 100 degrees under ambient pressure. But we have observed that as soon as the tiny product comes in contact with the distilled water, it immediately forms stable dispersion with a really high modulus zeta potential and really high concentration. Otherwise, we also try to treat this product with sodium acetate, and we obtain a result similar to what we showed before. So, how this synthesis actually work? Well, a possible explanation should be by considering the chemistry of iron citrate compounds, which is largely characterized in the literature and is really easy to find. So an iron citrate solution shows two plateaus in its rotation. The first one, this first one, is due to the formation of the nuclear coordination compounds between iron and citrate, where citric acid, citrate ions lose the proton in the oxidryl position. The second plateau instead is the polymerization of this dimeric coordination compound in a larger and heavier polymer. Nickel has a similar behavior, is less characterized in literature, but has been identified tetranuclear compounds, as well as some clustering compounds, and this can be related to this sloped plateau and the plateau at really high alkaline pH. So the filtration proof of our reaction mixture can be explained by the formation of some theoretically mixed coordination compounds that polymerize, and then after heating for 3 days, spontaneously hydrolyze and form the nickel iron LDH. So this can be monitored by the pH of the final solution, and we can see that the heating is pivotal to achieve the complete formation of the LDH by simply plotting the reaction mix, the reaction temperature versus the pH measured after 3 days. So let's say if we have actually obtained an LDH, because there are several key features to account. So the first LDH is our control synthesis is the urea hydrolysis synthesis. It produces really well-shaped hexagonal nanoplatelets with an average size 230 nanometers. Our synthesis with a slow sodium hydroxide injection lasted for 60 hours plus 12 hours of aging, so the total time is always 3 days, produced more rounded shaped platelet-like particles with an average size of 200 nanometers. While if we inject, we do a fast injection of the alkaline solution, after 3 days we obtain hexagonal shaped particles with an average size of 30 nanometers. Another way to verify the reaction, the formation of the LDH is the X-ray diffraction technique by depositing thin films of LDH onto silicon substrate. The characteristic diffractogram of LDH presents only 00L reflection, because those platelets tend to lay parallel to the substrate, and both diffractogram of carbonate LDH, which is our reference, and citrate LDH, which is our compounds, show those characteristic features, while the powder shows also other out-of-plane reflection. The important things to notice is that the 003 reflection is the lattice parameter 003 obtained by applying the Bragg equation to our diffractogram of the 003 reflection is the distance between one layer and the top of the subsequent layer. So one layer plus one interlayer space. We can see that this spacing increases by when the citrate is present instead of carbonate, and increases more if the film is made by the restacking of platelets dispersed in a solvent. You can compare the blue line here, which is the film obtained by a water dispersion of the nickel iron citrate LDH, by the red line of a water suspension, which is unstable because we precipitate, and the powder of the same compound. This assumption is confirmed by atomic force microscopy, which tell us that our reference material is made by platelets whose height is about 10 to 20 nanometers. This means from 7 to 10 layers to 20 layers, while the nickel iron citrate LDH presents nanoshift this time, because they are the thickness is between 1 and 1.5 nanometers, and so we can conclude that we have successfully chemically exfoliated the nickel iron LDH by incorporating citrate anions inside layers. So now let's come to electrochemical measurements. This material will be applied as a catalyst for oxygen evolution reaction for water splitting, since water splitting is the preferred technique to produce clean and pure hydrogen directly from water. So in our reaction condition, we are in alkaline solution. The hydrogen is produced by the reduction of water, while the oxygen, which is the reaction of our interest for this characterization, is produced by the oxidation of hydroxide ions dissolved in the solution. This reaction is quite sluggish because it involves 4 electron, 4 proton coupled reaction. And now we will see how our material performs. So the first parameter we have to consider is the resistance of the electrode. And we can clearly see that shifting from carbonate to citrate and to smaller citrate LDH, the resistance of the electrons diminishes. Then we check the overpotential required to achieve 10 millivolts of current, and we see here a contrasting behavior with the resistance, but it is not so much. Why? Because a more alkaline anion inside the hydroxide layer facilitate the loses the water splitting procedure by facilitating the oxidation of nickel that we will see later. And then the other thing we can see is that reducing the size of the particles dramatically reduces the overpotential required. This can be related to the higher amount of edge size in the smaller platelets. And same thing as the tough slope. The slope follow the same trend of the overpotential, but we can notice that the smaller particle has two slopes, one at lower currents and one at higher current. This is can also be related to the saturation of edge sides on the smaller particle. In fact, when they are saturated, the tough slope is pretty similar to the larger particle of the LDH. Finally, the turnover frequency is the number of oxygen molecule, average number of oxygen molecules produced per active site, can be easily calculated by some mathematical substitution in the equation of turnover frequency, in which J is the current density, Avogadro's number, 4 is number of the electrons involved. The density of active site, the Faraday number, can be related to the number, to the charge under the characteristical nickel peak in the cyclic voltammetry. And so, as we can see, also the turnover frequency follows the trends shown before. The second characterization we have done, we have concluded that the nickel iron citrate LDH with here's wrong 30 nanometer size is the one with lower resistance. We applied it with for supercapacitor. The charge storage mechanism is the same of nickel hydroxide, widely used in batteries. So we prepared an electrode on nickel foam with our LDH, and we see that the mechanism of charge storage follows a diffusion controlled kinetics simply by plotting the square root of scan speed versus the maximum of current achieved. Then we combined our LDH with carbon black in a composite and we deposited on nickel foam, and we observed that there is a significant improvement of performance of the capacitor. This improvement is also observed in charge curves, when we can see that the carbon black nickel iron LDH composite has almost 3 times the specific capacitance of bare nickel iron LDH. At least I want to add one more characterization to this presentation, is the glucose oxidation, since nickel compounds are known to be active to oxidate small molecules. Our LDH showed a pretty linear response to glucose with a good sensitivity, almost 500 times that bare of graphite. And here we arrive to the conclusion. So we have developed a new synthetic route to exfoliate nickel iron LDH in cheap and green solvent. Then we tested our compounds with promising result for water splitting, asymmetric supercapacitors, and glucose oxidation. I must thanks collaborators that helped me for in this project, and I thank you for listening.
Okay, thank you very much, Marco, for your.
Wait, how do I? Okay. Okay.
Okay, thank you very much, Marco. So do you have any question? It's very interesting presentation, very interesting material. No question? We have not much time. We are slightly late, not so much. And so I would like to ask you a very simple question concerning the electrochemical characterization, in particular for the water splitting reaction. So did you also characterize the products of the oxidation? So you actually measured the amount of oxygen that evolved during the process?
Unfortunately not, because we don't have the equipment for that.
So you are assuming that you have 100% oxygen evolution?
No, we are not, because from the literature, this material is not so new. The carbonate one is well known. The efficiency is about 98%. Okay. But we don't know how much is the efficiency of our citrate one, because we don't have the equipment.
And do you think you might also have some other process to explain why you have a change in the toughest slope with one of the three materials that you?
Yeah. Okay. So this is a quite complicated topic, because the toughest slope can change because changes the active site, but also because changes the rate determining step. So maybe we have only the edge active sites that are saturated in the 200 nanometers particle from the beginning, and while in the 30 nanometers particle are not saturated at the beginning, and we saturate that active site. Or we have the active sites saturated in the 200 nanometer particles and the surface size as well in the 30 nanometers. So this is hard to tell. Maybe the electron tunneling can the electrochemical can answer this. However, it should be really hard to synthesize perfectly isolated and flat flakes, because as you saw in the TM images, they tend to aggregate when placed on carbon or silicon.
Okay. Thank you very much. Any other questions? No, apparently no question around. So let's thank again the speaker and all the speakers of this session. I was very happy to chair this very interesting session. And now we have the coffee break, and then the afternoon session will continue with another series of very interesting talks. Thank you very much, and goodbye.
So, good afternoon, ladies and gentlemen. Can you hear me? I hope so.
Yes.
And let's start with the last part of the session 2, that is dedicated to advanced material for energy conversion and storage. And after the very interesting lecture that we have listened today, we will, I'm sure, we will finish with a further very nice lecture. We are programmed 5 lectures, 1 keynote and 4 talks. The first one will be delivered by Erika Michela De Matteis. She comes from the University of Turin. This is a presentation done by Erika, together with David Dreistat, Giovanni Capurso, Julian Jepsen, Fermin Cuevas, Michel Latroche, and Marcello Baricco. The title is Titanium Iron Substituted Intermetallic for Large-Scale Stationary Hydrogen Storage. Please, Erika, try to stay in time and start with your presentation.
Welcome everybody, and thank you for the opportunity to briefly give you an overview of my research activities in the frame of titanium iron substituted materials for large-scale stationary hydrogen storage. The motivation behind our research work is that hydrogen is in the middle of a new enthusiasm wave. And basically, by using hydrogen and hydrogen technologies, we can fence climate change. And climate change can be an important driver also for the widespread use of clean hydrogen. And that's basically because hydrogen is a really good energy vector, and it can help in the rapid growth of renewable energies, helping us in reducing emissions. Hydrogen can also benefit from a really large experience in developing clean energy technologies and can contribute to a wider range of policies objectives. The ICAR project is the project on which is based my research activities, and the goal is that we want to take care of hydrogen storage and hydrogen technologies by storing approximately 50 kilos of hydrogen in mild condition and make it real by synthesizing almost 5 tons of metal powder in which the hydrogen will be stored safely in the solid state. The thermal management of the integrated system will be performed with innovative technologies using phase change materials. And this will allow us to improve efficiency and also have a low footprint. Furthermore, we will make it possible to extend the use of renewable energies and to store renewable energies and demonstrate this integrated system for large-scale application in the Living Lab of ENGIE. The integrated system will be installed in the middle of 2022. The material that has been selected for the project is based on iron titanium intermetallic compound. And that's because basically iron titanium are really low-cost materials. They can have high hydrogen capacity up to 1.8 in weight percent at 25 degrees C. However, it still requires harsh activation. So the first hydrogenation it's performing in harsh condition of pressure and temperature. The iron titanium intermetallic can be synthesized in a range of titanium composition, and as it can be observed from the pressure composition isotherm in the graph, basically we can move from the intermetallic phase that has a cubic structure. We can hydrogenate this phase through the formation of a solid solution to form the alpha phase, and then we observe a first plateau pressure at which we have the formation of the monohydride that has a orthorhombic structure. And then just at higher pressure, we can observe a second plateau to form the complete dihydride phase that is called gamma phase, again with an orthorhombic structure. This material can be also easily tailored by introducing different elements, substituting either iron or titanium. And we recently published a gold open access paper in which we collected all the literature data available on substitution effect in titanium iron. As you can observe from the periodic table, basically all the green elements were explored. However, we need to also take into account, once we selected our material, that we should not include critical raw material for Europe. Unfortunately, last year, titanium has been included as critical raw material for Europe, basically because it's imported. However, it's still a low-cost material and can be really a benefit to develop hydrogen storage technologies based on this intermetallic compound worldwide. We decided to focus on the iron titanium manganese system, basically because it was already reported in the literature that we can play with tunable plateau pressure, so we can tailor the composition and also the hydrogenation property as a function of the composition. and as a function of the final application and region pressure and temperature we want to take into account. It was already reported that manganese can substitute iron, enlarging the cell parameter, which means also decreased plateau pressure, easier activation at lower pressure and low temperature, and also fast kinetics. So improving also a lot the hydrogenation properties of the material. Furthermore, decreased plateau step between the first and the second plateau can be observed, and this means that we need a lower range of pressure to fully hydrogenate our material. So during our exploration, we basically synthesize our material by induction furnace, by annealing the material at 1 week at the lab scale at 1000 degrees C, and then we characterize our material by X-ray, electron microprobe analysis, and also by Siever bank to activate the sample and also determine the hydrogenation properties. The compositional mapping that was performed took into account 9 different compositions, and the microstructural characterization evidence the formation of secondary phases in some of the material. Basically, the microstructural analysis and compositional analysis evidenced the formation of the largest phase, that was the titanium iron matrix, while the secondary phases were observed as titanium iron 2 in the case of the right side of the phase diagram, so in sample S1, 3, 4, and 8 especially, while on the titanium-rich side of the phase diagram, titanium-rich precipitate were observed, and also the formation of an oxide phase. The compositional balance suggests that the titanium-rich, so titanium and manganese, substitute iron in the structure. The structural characterization done by X-ray and also by refinement evidence, as reported by the counter map in the graph, the formation of the different phases and also a larger cell parameter as a function of the amount of titanium and manganese in the composition. Approximately 1 to 4 weight% of oxide phase in titanium-rich compound were observed, composition, and 2 to 5 weight% of the beta titanium-rich phase was also observed in this kind of composition on the right side of the phase diagram. The activation and the kinetics of the 9 different compounds were quite different. What we observe is still to have harsh conditions, so high temperature, 400 degrees C, and high pressure, 5 megapascal, required for the first activation of 1-to-1 composition, so on the right side of the phase diagram. While introducing titanium and manganese, the lower hysteresis in absorption and desorption was observed. And still, good reversible capacity are obtained in mild condition for almost all the composition. The thermodynamics observed by APCI curve reported clearly detects first and second plateau in 1-to-1 composition, while there's a smoothing effect of the plateaus while introducing manganese, as reported already in the literature. Good capacity is retained, and reduced hysteresis with titanium and manganese can also be observed from this characterization. A linear correlation between the logarithm of the plateau pressure and also the titanium iron cell volume was clearly observed for the first and second plateau on the absorption at 25 degrees C. And this means we can basically play with the substitution, the composition, and the cell volume of the structure to also select an appropriate plateau pressure for hydrogen absorption and desorption in this material. The conclusion and outcome on this work is that basically iron titanium intermetallic is a cheap and promising material for large-scale application. There's a dependency on hydrogenation properties over an extended titanium and manganese compositional range, which was evidenced in this study. And also the plateau pressure can be tailored as a function of the element introduced in the BCC structure. The plateau pressure varies linearly, so we can clearly choose the right composition, and then the sample at the titanium-rich side have enhanced storage reversible capacity and also activation properties. So they can be hydrogenated in milder condition, And basically, sample number 6 has a best compositional trade-off and still retaining high capacity, 1.6 at 25 degrees C and at 30 bar, and also easy activation with good kinetics. The study has been published in a Green Open Access paper, and also we extended the study to quaternary composition, introducing also copper. And copper basically substitute iron as well, enlarging the cell volume and also reducing the first plateau pressure, while moving to higher plateau pressure the second one. So in the case of copper, it can be promising for low pressure storage with a bit less capacities. The outlook of the work is to also have a look on this in situ neutron diffraction studies to evaluate structure evolution during hydrogenation, loading and unloading. I just want to conclude, acknowledge all the partner of the ICAR project and all my group at the University of Turin, and all of you for the kind attention.
Microphone, please.
Perfect. So I just thanks Erika for this brilliant presentation, very clear, very detailed, and very interesting. And I would like to start with some questions from the audience or curiosities. Please. Is there any there ready for questions? So I will just start with a curiosity. You discussed, you mentioned that titanium has been declared a sort of a critical material. And that's, in my opinion, quite curious because a large part of our planet is done by titanium. Can you comment a little bit to this point?
Yes, thank you for the question. Basically, it was introduced as a critical raw material in the list of critical raw material for Europe last year in 2020. And that's basically related to the fact that Europe does not have really a large amount of titanium, which is available in the country. And it has a kind of importation market on which Europe needs to depend on. So that's why for Europe, titanium right now is a bit critical material. While, for example, in Japan, this is not so critical because it's widely available. And so for this reason, we do believe that still this kind of material can be really promising for developing hydrogen storage technologies worldwide and not only in Europe.
Yes, thank you, because otherwise you just break one of our certain point of the life, that titanium like silicon are iron and so on are not real critical material. Well, so any other questions or curiosities from the audience? We have just 1 minute, just one point about your manganese component in these nice alloys. As an homogeneous chemist, I know that manganese hydride are, let's say, not particularly common. Which kind of manganese hydride phases do you think are relevant in this chemistry?
So in this case, manganese actually is substituting iron inside the composition of the iron titanium intermetallic phase. So basically is not forming manganese hydride, but is still the titanium iron hydride which is forming. However, the possibility to change it, to tailor the composition is quite interesting because allows us to modify the thermodynamics of the material and thus the plateau pressure and also the hydrogenation properties can be improved or tailored as a function of the application we are looking for. So in the case of manganese is basically lowering the plateau pressure of the hydride, making it more stable at lower pressure. And that was really beneficial for our project.
Okay, so thank you. Thank you again for your presentation.
Thank you.
And let's move to the second speaker. that came from Florence, to be frank, Sesto Fiorentino in Florence, Dr. Andrea Marchionni. Is Andrea online? Andrea will talk about hydrogen. Ciao Andrea, good afternoon. Andrea?
Afternoon.
Okay.
I am Marchionni.
Do you hear me?
At the Institute of Chemistry of Organometallic
Okay,
Compounds.
it started. Please go on.
Good afternoon. I am Andrea Marchionni. I am working at the Institute of Chemistry of Organometallic Compounds on electrocatalytic systems. Today, I will talk to you about recent results on new topological materials, platinum-tin 4 and palladium-tin 4. In this presentation, I will briefly show you why these materials are attracting interest in electrocatalysis, in particular towards the hydrogen evolution reaction. Why topological materials? These kind of materials have a unique valence and conductive energy bands that is similar to graphene. In particular, topological direct semimetals showed properties that can be toned by chemical composition and spin orbital coupling strength. Among Dirac semimetal, platinum-tin 4 and palladium-tin 4 are attracting high interest because of their relative low noble metal content, about 30% of platinum and 18% of palladium, and their potential use as electrocatalysts towards many reactions, for example, hydrogen evolution. The synthesis of platinum and palladium-tin 4 was made by a self-flux method in which the noble metal was quickly heated in a large amount of tin, following the Hahn diagram phase. After, the material was quickly cooled down to 350 degrees and then was slowly cooled down to until 250 degrees. Finally, the excess of tin was removed by centrifugation and the obtained alloy was purified in hydrochloric acid solution. The surface composition has a crucial role to determine the electrochemical behavior. Then, the first issue to be solved was the surface determination of these materials. Calculation suggested three possible configurations. The first showed a single layer of platinum atoms. The second, 2 layers of tin atoms. And the third showed 1 layer of tin atoms on both faces. The results on energy calculation on all of them indicated that the most stable configuration was the last one. This was also confirmed by electron microscopy and energy-dependent and angle-dependent XPS experiments. Same results were obtained for palladium-tin 4 also. Who use noble metal-based catalysts knows the importance of their resistance towards CO poisoning. Then we test it, made XPS experiment in CO dosed atmosphere. The results showed that both alloys were fully tolerant toward CO adsorption. Now we pass to the electrochemical characterization. Both platinum and palladium-tin 4 had a behavior similar to poor noble metals than poor tin. This seems in contrast with the previous results on the surface termination, but deep investigation had clarified this unexpected behavior. First of all, we made cyclic voltammetry experiments varying the upper limit of the potential window, and we observed that hydrogen evolution performances, both in terms of onset potentials and current density, was improved by exposure to oxidative potential. Indeed, the plot of the current density increments towards the upper limit potential window showed a critical point around 1.1 volt versus relative hydrogen electrode. This improvement was verified also by Tafel slope determination. In particular, pristine surface showed a high slope value typical of sluggish kinetics. Instead, after the oxidation treatment, the slope decreased to value similar to platinum foil. This was suggesting a changing in the catalytic pathway. The same behavior was also observed for palladium tin-4 also, although with lower intensity. Calculation on catalytic mechanism found that more favorable hydrogen evolution reaction pathways were identified on oxidated surface on both materials. Furthermore, hydrogen evolution was successfully modeled with a combination of Volmer and Tafel mechanisms. Scanning electron microscopy was used to investigate changes on the morphology of electrode surface before and after the electro-oxidation treatment. In case of platinum tin-4, the comparison of secondary and scattered electrons showed that there was a formation of cracked layers, showed a lower density than other parts. This suggests the formation of oxidized species on the surface. In the case of palladium tin-4, the pictures were recorded before and after an accelerated aging treatment made by 5000 cyclic voltammetry. We used two upper limits of the potential windows, 1 volt and 2.2 volt versus relative hydrogen electrode. During the first experiment, the electrochemical behavior remained quite stable and the surface showed limited damages and morphological modification. The second experiment with the broader potential window showed a fast decay of the electrochemical performance. Furthermore, the picture showed high damages and morphology changes on the oxidized surface with the formation of large rough area. The formation of oxide layers was confirmed by ADX experiment on the edge between rough and smooth area, respectively in the upper and then the bottom side of the picture. The results shows the high oxygen content in the upper area that agree with the formation of oxidized species. Also, XPS experiments before and after the electrochemical oxidation treatment confirmed the formation of the oxidized tin species. Also, palladium was oxidized, but there was also probably a contribution due by palladium 0 also. This could explain part of the electrochemical behavior. Finally, we investigated the topological state role in hydrogen evolution reaction by electrode surface modification with the iron phthalocyanine. We chosen the iron complex for its ability to modify topological states as reported in the literature. The cyclic voltammetry showed that iron phthalocyanine modified electrode had a behavior similar to pristine electrode, although a lower current density due by covering surface. These results suggest that topological states were not involved in the electrocatalytic hydrogen evolution. In conclusion, we found that platinum tin-4 and palladium tin-4 surfaces terminated with one layer of tin atoms and was confirmed by electron microscopy. Furthermore, the materials result resistant towards CO poisoning. The electrochemical behavior of these materials was similar to poor noble metals than poor tin, despite their relatively low content. an electron oxidation treatment improves the hydrogen evolution reaction, and this can be well modeled by a combination of Volmer and Tafel steps. Finally, all the results suggest that topological states are not involved in the electrochemical hydrogen evolution. In the end, I will thank all my colleagues, the other research involved in this study, and all the audience for the kind attention.
Thank you, Andrea. Thank you, Andrea, for this very precise and interesting presentation. The stage is yours for answering questions that I would like to raise from the audience. Questions or curiosities, please.
Hello, I'm Alessandro Molle. So I have a question for Andrea. Hello, Maurizio.
Ciao, Alessandro.
I'm curious to know why topological insulator or any kind of topological materials could be interesting to enhance the hydrogen evolution reaction. What is the key mechanism that makes them appealing for this kind of functionality? Do you have an idea in mind?
Well, this is a field study on this material because these materials are very interesting from a theoretical study on that explain why topological material can be involved in a catalytic system. So our curiosity was to study this theoretical improvement in electrocatalysis, and we test the hydrogen evolution reaction because platinum and palladium are noble metal that are the state of the art for this reaction.
I agree, but if you have a compound based on tin, you know that tin is going to be oxidized quite easily. So that if you get oxidation, so I don't understand. It's not clear to me how to make use of oxidation of oxidized tin to make an electrocatalysis, as you say.
Well, so we saw that tin was oxidized in the electrolyte. So just to put the metals, the materials in the electrolyte, in the solution, tin was oxidized. So the electrochemical, to apply the potential easily oxidized tin, and we saw that also palladium and platinum can be oxidized also. So tin is a common diluent in this case, and it can decrease the amount of noble metal, but the electrochemical system remains quite stable as the noble metals, as pristine noble metal.
It's okay, Alessandro?
Yeah, sure.
Okay,
thank you.
Thanks. So time is flying. We are just at the end of the time allotted to Andrea, that I would like to thank again. And I have a question, but I will do this in a separate and private area when we will meet. So thank you, Andrea. And
thank you all.
Move to the next speaker, which is a distinguished keynote lecturer. Sorry, no, is Emanuela Mastronardo. Emanuela Mastronardo. Good afternoon,
I'm here.
Emanuela.
I'm here. Can you hear me?
Yeah, we hear you. I just introduce you, just saying that you are working in Spain, in Madrid, at the Consejo Superior de Investigación Científica, al CSIC, and this is a, let's say, presentation that you share with colleagues from Messina and Evanston in the United States. The title is a Thermal Energy Storage Reactor test on iron-doped calcium manganese. Please try to stay in time, as we are respecting perfectly the schedule. You can
Good
start.
afternoon, everyone. I'm Emanuela Mastronardo, and I will present the results of a thermal energy storage reactor test on iron-doped calcium manganese oxide. Solar energy, being it free and endless, is an attractive source of energy that can be converted into electricity by means of a concentrated solar power plant. However, the biggest limit of such technology is the intermittency and the diurnal nature of the solar light itself. So for the future developments, CSP plants need to be coupled with a storage system. And finding an inexpensive, efficient means of storing energy produced by a CSP plant would be a milestone for the fast growing of the renewable energy sector. So at this purpose, thermochemical energy storage systems can directly store solar energy produced by CSP plants during on-sun operation mode, as it can reuse it on demand during the off-sun operation mode. In this study, perovskite ABO3 have been investigated as thermal energy storage materials, and the working principle of a thermal energy storage system that is based on a perovskite consists in the following reaction, where basically the heat is stored during the endothermic reduction, and the oxidation, being it exothermic, releases heat when it is required. The amount of reversibly exchangeable oxygen is a function of temperature and of the oxygen partial pressure. So the total heat storage capacity consists of two terms, the chemical heat and the sensible heat. Perovskites can release oxygen upon either an isothermal decrease in oxygen partial pressure or an isobaric increase in temperature. Although the change in oxygen stoichiometry can be theoretically made by the same in the isobaric and isothermal cases, in the latter, the very low pressure required are impractical. So at the industrial scale, reducing the PO2 beyond 10 to minus 4 atmospheres incurs a significant energy cost. So an isobaric operation under fixed technologically feasible PO2 is the likely mode by which non-stoichiometry oxide can be implemented. There are several requirements for a material to be an ideal candidate for thermal energy storage, like the complete reduction reversibility, and the material should be cost-effective and made of earth-abundant elements, especially high energy storage density. That in the case of a perovskite means high reduction and oxidation enthalpy and large reaction extent. But in reality, high reaction enthalpy is associated to a small reaction extent. Vice versa is also true. So we need to find a compromise between the reaction enthalpy and reaction extent in order to find a suitable candidate for this application. Calcium manganese oxide is a potentially interesting candidate material because of its reaction enthalpy and reaction extent, being also made of earth-abundant, inexpensive, and non-toxic element. However, its use is limited because of its poor thermal stability under relevant operating conditions. However, the material's properties can be modified through the doping mechanism, and here we investigated a 10% iron-doped composition. The 10% iron-doped composition showed a larger enthalpy with respect to the undoped material, enhanced thermal stability, and good durability to several reaction cycles. These results warranted further investigations with a larger reactor scale. So for the reactor test, about 50 grams of pellets of 10% iron-doped calcium. So first of all, the powder has been synthesized through the Peccinis method, and obtained CMF91 has been mixed with cellulose with different amount, mixed and grinded and wetted with water, so that a moldable paste has been obtained and extruded, like showed in the picture, and kept it into small pieces that were then sintered at 1100 degrees C under static air. So the pellets have been characterized through scanning electron microscopy, mercury porosimetry, and reactor tests, of course, have been carried out. The laboratory scale reactor tests were carried out in this apparatus shown in these figures, which consists basically in a furnace, in a high temperature furnace, and an alumina reactor filled with some alumina, with an alumina bed, upon which the pellets of the materials have been located in the middle part of the reactor. So different conditions were tested, like different ramp rate, flow rate, oxygen partial pressure, and reduction temperature. The oxygen evolution profiles of the materials during the reactor test have been collected through a micro-GC, as can be observed here in figure, as a function of time and temperature. And the oxygen on stoichiometry profile has been determined through these equations. So the use of 5% of CMC for the pellets preparation allowed obtaining a 50% of porosity, that is enough for the gas to flow through the pellets. And the selected amount is enough also to prepare a moldable and extrudable paste to obtain smaller pores, allowing a more robust structure. Indeed, sufficient mechanical strength of the pellets, it is a prerequisite for their use in a bed reactor. Remarkably, the material showed the same oxygen on stoichiometry profile during heating and cooling when operating at the gram scale in a more realistic reactor than when measured at a much smaller scale in the initial assays for the determination of the thermodynamic properties of this material. It can be observed from figure A. At the different ramp rates, the heating profiles almost entirely overlap. Now, however, the conversion profiles during cooling is slower the higher the ramp rate is. This result implies that the 7 and 10 degrees C per minute cooling rate were too rapid to allow the material to remain in equilibrium conditions during cooling. On the contrary, the gas flow rate has a very significant impact on the oxygen evolution profiles. Indeed, while decreasing from 8 to 2 normal liters per minute, the material underwent continuous mass loss during a brief isothermal hold at 1200 degrees C, and the larger oxygen on stoichiometry is accessed with respect to the other conditions. Additionally, a larger hysteresis is observable between the heating and the cooling profiles. Such results implies that these last experimental conditions did not allow the material to remain in equilibrium conditions during the dynamic steps of heating and cooling. So ideal conditions for this system to work are 5 degrees C per minute under a flow rate of 8 normal liters per minute. The material operating in a temperature range between 500 and 1200 degrees C and under a PO2 of 0.01 atmospheres has a total heat storage capacity of about 916 kilojoule per kilogram of material, but it can also work at milder conditions, that is 500, 1100 degrees C under a lower PO2 of 0.001 atmospheres, getting a total heat storage capacity of 670 kilojoule per kilogram of material. So after tests, the material has been discharged from the reactor and characterized through XRD analysis and mercury porosimetry. The pellets result almost entirely intact after testing with just a little formation of fines. X-ray diffractions showed no secondary phase caused by decompositions into spinel and Radon Popper structures due to irreversible reaction. In the material discharge also from the bottom part of the reactor, some alumina impurities have been detected, most likely due to the contact between the material and the alumina bed. While the average porosity, as well as the pore volume area and density, significantly decreased after test, and the average pore size is shifted towards notably greater values. So this is likely can be explained considering that after several thermal treatments at temperatures above 1000 degrees C, the pellets underwent some sintering effect, reducing the number of smaller pores and increasing the larger ones. So in conclusion, the 10% iron-doped calcium manganese oxide at a significantly larger scale exhibited the same performance than the one extracted from its thermodynamics. No energy loss is obtained due to unreoxidized or decomposed materials, and these materials offers a total storage capacity of about 900 kilojoule per kilogram in a temperature range between 500 and 1200 degrees C. So this material appears ideally suited for thermal energy storage applications with a large total storage capacity and a good scalability. So this project has received funding from the European Union Horizon 2020 Research and Innovation Program. And I would like to acknowledge the project supervisors, Dr. Juan Coronado from the Institute of Catalysis and Petrochemistry of the CSIC in Spain, Professor Susina Aile from the Material Science and Engineering Department of Northwestern University, and all the collaborators to this project. I would like also to thank the committee for allowing me to present these results to this conference, and also all the audience for the kind attention.
Thank you, Emanuela, for this nice presentation. We have just a couple of minutes left. So if there are questions or curiosities, please introduce yourself and make the question. Apparently everything has been quite clear. No question at all. So,
Okay.
Emanuela, thank you so much.
Okay, it was a pleasure.
Thank you.